Great. So we're back now for the other type of differentiation questions that come up in past papers that you should know, and these are related to the applications. Okay, these are application-based questions, and there are a lot of these come up on paper one, and some of them make their way even onto paper two. So you can see here there's 121 questions, and there's 216 pages in this PDF. Now I've gone through it all, and I've kind of put X's beside sort of the stuff you're meant to know. Okay. So we're going to get straight into it because there could be a bit of time involved in getting through all this. So we look at the first question here. So the main part of this question that I want to do is this here where we get the area between the curve. That's actually an integration problem, but the build up to that builds in some differentiation. So we'll just push through this as quickly as we can. So as always, when I'm kind of about to do a problem, always pause the video and give it a go yourself because you'll get the most out of the videos that way. Okay, so let's get straight into it. So we have some function. It's a nice straightforward quadratic, and we're told to find the derivative of it. That's no issue at all. F dash x here is 2x over 12, which is basically just x over 6. Okay. The tangent to f of x at this point m has a slope of -2. Find the equation of this tangent. Okay, so basically we should know that f dash x is the slope of the tangent. Okay, so then they tell us the slope of the tangent here is -2. That means that f dash x at this point m is -2. So we set that equal to our x over 6 we worked out, and we can see there that x is -12. Okay, now we do need m as a point. Okay, so we're missing its y value. We get its y value from subbing into f of x because f of x is y. We should all know this. So y equals x minus 12 squared over 12, and so y then equals a plus 12. So m as a point is -12, 12. Okay, so then to get the equation of this tangent, what we do is I'll use a different color here. Y minus y1 equals m times x minus x1. We need a point and a slope. We have the point and the slope of that black linear line. So we go y minus 12 equals the slope of -2, and then it's x minus -12, so that turns into a plus 12. And so you go and you multiply all that out. Y minus 12 equals -2x minus 24. Bring it. So they want it this way where y is brought on its own. Usually we bring them all to one side, but not when they request it like this. So they want it to be left as y equals -2x. The 12 comes over, it's plus, so that's -12. Okay. And yeah, so we have a linear line with a slope of -2, and it intercepts the y-axis at -12, which looks like it's going to happen down there. Okay. Great. So then the next part of this question, they give us the diagram again, so let's rub away some of this stuff. Okay. Show that the equation of the tangent, the line perpendicular to the tangent passing through M, can be written as this. Okay, so the point here is, this is just kind of coordinate geometry line. The slope of this tangent here was -2, and any line perpendicular to that, you flip the slope and change the sign. So you change the sign, it'll become +2, and then you flip it. So the slope of this line, the perpendicular line, is a half. And it still goes through M, which is this point here. So you just make a brand new, use y minus y1 again. So my minus y1 equals m times x minus x1. So this was a pretty easy question to get us going. The questions are going to get a bit more intense as we get on from here. But this is something that everyone should be able to do because it's a pretty important question, this, at the end of the day, for what can come up on the application. So then it's x, and then again it's minus, so it turns to a plus. Right, so what we'll do here is we get the y on its own again. So y minus 12 equals x over 2 plus 6. And then it's y equals x over 2, and then it's a plus 18. And that's what they've got there. And yeah, so that's going through 18 there. Okay, because that's the c. We're across the y-axis. Okay, so we're basically asked now to get the area here between the line and the quadratic. Now to get that, we need to get this point n, but they don't tell us that we need n, but we do need n. Right, how do we get n? N is where the line, this purple line, intersects this quadratic. Okay, and the easiest way to get that, to get the point of intersection, is just set the two y values equal to one another, because that's like a way of solving a simultaneous equation. So we get this by going x squared over 12, setting the quadratic equal to the linear's y value like this. And this will find the point of intersection of the two curves, 18. So we'll multiply everything by 12. So we get x squared equals 6x. What would 12 by 18 be? 12 by 18 is 216. 216, so then we get x squared minus 6x minus 216 equals 0, and we can definitely factorize that. It looks a bit nasty though to factorize. Factors of 216. So I've got lucky there. It looks like 12 and 18. So I'd go for minus 18 and x plus 12. So the two x values are x equals minus 12, which was m's point, and then the main thing is x equals 18 is associated with n here. And all we need to get is its y value. So a quick way to get its y value is you can put it into either the line or the quadratic, but I'll put it into the quadratic. So y equals 18 squared over 12, which is 27. Okay, so the y value there is 27. So m's coordinates, there's a lot going on the screen, but the m's coordinates, n, is 1827. Right, so I'm going to clear a lot of stuff away here now, because I've got what I need now. So I absolutely recommend people have a go at part 2 here, see if you know how to do it. So the idea is here, let me state m and n again here. So I think this was minus 12. This here was 1827. Right. If you want to get the area between two curves, in other words, the linear and this quadratic, what you do is you subtract the two curves and then you integrate, and that gets you the area between them, okay? So what we call that the area enclosed. And you get that between two curves. So let me, because in case you didn't know this, you can make a flashcard on this, between two curves. Right? So what you do is you only have to integrate once, and you'll integrate between the 2 points. There'll be a point here and a point here. We're going to talk about that in a second. And then what this is going to be, you're going to be like, we can make it, it's like f of x take away g of x, we'll say. F of x take away g of x. Yeah, so I actually wanted that there, respect to dx. And this, you could say it's going from point, say, m in this question up to point n. Okay? So that's what you always do. So you just take away the two equations and then you integrate once, and that gets your area enclosed. So let's do this. So what we do, though, first the curve that you always take away from the other, who's ever the tallest one. So you can see the line is the taller one, and it's the quadratic that's underneath it, okay? So what we do here, and we're going to integrate, it's always between the x values. So this guy's x value was minus 12, and this guy's x value is a plus 18. Okay, and we're going to integrate, basically, the taller graph is this function here. So we go x over 2 plus 18, take away the lower curve, which is this, which is x squared over 12. And all of that is with respect to dx, okay? So that is what we're looking for. And when we basically integrate that, we're going to get our answer. So what I'm going to do is I'm going to make some room for myself here. Okay. So let's do this integration. Yeah, you could basically just integrate this straight away. There's no need to kind of take anything away. So I can basically just say the area here. I'll call it area now because we know it's the area enclosed. We can change this to a straight line because we can do the integration. So x over 2 integrated becomes x squared over 4. Hopefully you're okay with that. This becomes 18x, and this will be a minus x to the 3 over 36. Okay, I think I've integrated that correctly. Looks like it. 18 x squared over 2, yeah. So you can always quickly differentiate it again in your head to make sure that it goes back to the original thing up here. So then what you do here is two square brackets where you put the top limit in first. 18 squared over 4 plus 18 times 18 minus 18 cubed over 36. Take away when the lower limit's in, you got to be careful. This one is a minus sign. So it's going to be minus 12 squared over 4 plus 18 bracket minus 12 minus 12 cubed over 36. Now that's pretty intense to type all of that into your calculator, but know this, that what you have there in that lower green line picks up most of the marks. You get like 14 out of 15 marks basically for having that. You get like an extra mark for being able to type it into a calculator. So I'm going to pause the video and have a go typing that into a calculator. Okay, so when I typed that in there, I got that the area basically works out to be 375 square units. So again, hopefully that's correct, but the main thing is this is correct down here, okay? So that's definitely something for your flashcards. Area enclosed, take away the taller curve from the lower curve, and then just integrate once between where the points intersect, where the curves intersect their x values. Okay, so that was actually a really good, important question. So let's go into two-page format here, and let's scroll along now. And let's find our next red dash. Okay, so I might, when I'm looking for these, because it's such a big PDF, I might pause the video in the future and then just kind of jump to it, you know. So we got this here. Okay, so this seems to be like its own kind of isolated question in E. So of course, pause the video, give it a go. So the derivative of some function called c of t is given by this. Find the value of t that gives the first local maximum. See, that is the first time that c of t equals 0. Now that's a massive hint, okay? They nearly shouldn't be telling you that. You're supposed to kind of be able to suss that out yourself, okay? But anyways, we'll work out what we're doing. So like they've told you the thing here, if you want to find max and min points, what you do is you take a derivative of c dash t, you get that, and then you set it equal to 0, and this will get you your max and mins. So the idea is here we have 0.03 minus 38 pi over 365, and we have sine 2 pi t over 365. So I have a feeling where this is going to be one of these where you get two answers from solving this. So I would have covered a lot of this in the trigonometry videos that are on the YouTube channel. So if what I'm doing here is a little bit confusing, you'll see loads of these solved in the past paper questions from the trigonometry video if you have a scroll through the channel. So basically I'm moving this around and getting this sign on its own first. So then sine 2 pi t over 365. So you multiply up by the 365, so the signs will go, they're both negative, so it'll just become positive, everyone. This is times 365 all over 2 pi. Now what I'll do is I'll simplify that to be a number. 0.03 multiplied by 365 over 2 pi. Yeah, that number should be less than 1. Let me see what I've missed. So there's a 38 pi. So I knew there was something wrong there. I'll explain how I knew there was something wrong there. So there was something wrong there because this number was bigger than 1, and sine can never give a value bigger than 1. Okay, so that was a hint. Something was wrong. How did that turn into a 2 pi? It's me being silly. Okay, so then this is 38 pi. So now, yeah, so that number is not bigger than 1 now. Okay, so then this is solvable. So we have sine 2 pi t over 365, and I'm getting that equal to this number here. We want a few decimal places on this as well if we want an accurate answer. I'm going to go 9172. Okay, that's probably enough. Now, what you want to realize here is this is sine equal to this positive number. So, as I said, I've solved these before. So if this doesn't make sense what I'm doing here, go have a look at them trigonometry past paper questions on the YouTube channel. So there's two places where sine is positive. It's positive in here and it's positive in here. So I want the answer in here. This will be like a theta answer, and then we move it over to this quadrant with pi minus theta. So what we do is we take sine inverse. First of all, you kind of split the page down the middle. So I want some room for doing this. So that this guy can move over here. And let me get another color out, because this is pretty important for people. So you split the page down the middle. So you're going to get something like 2 pi t over 365. I'm going to take a sine inverse of this. So sine inverse 0.09172. So that's going to give the first quadrant answer which we want. So sine inverse 0.09172. And that gives this decimal answer 0.09185. And if I had room, I'd be putting this over here, but what I'm going to do is I'll split the page vertically here. So the other scenario is when this is our theta here. What we do is we go pi minus that, okay? So that's equal to pi minus that number. You want to show the workings like that for your examiner. So basically it's just a matter of move this around, multiply this by 365 divided by 2 pi. 0.09185 multiplied by 365 over 2 pi. And the first one there is 5336. Is there units on that? T might be in hours or something, you know, or days. They didn't tell us the units here. It would have been mentioned earlier on in the question. So then we go pi minus 0.9185. Multiply that by 365 divided by 2 pi. And you get this other one, which is 177.164. Okay. So the idea is there are two t values. Now one of them gives a maximum and one of them gives a minimum. Okay, so they're for the two turning points. So how do we work out which gives the max and the min? So there's two ways to do this. Right, there's two ways to do this. So the ordinary level maths way of doing this, and it would absolutely work for this question, is you just put t back into the function here, and you put your both t's back in, and whichever one gives the bigger value will be the maximum, and then the other one that gives the small value is the minimum. But at higher level maths, we're supposed to know that you get to do this something called the second derivative test. So yeah, something called the second derivative test. And so that's when this thing is greater than 0. It's a little bit counterintuitive. When it's greater than 0, that's the min. And when c dash t is less than 0, that's the max. Okay, so if we want the first local min, and we'll explain what it means by first local min. So because this thing is a trigonometric function, it's going to keep doing like zigzags like this, you know. So there'll be a local min here, but then in the next period, there'll be more local mins, you know. So we want really just what happens in the first period, all right? So hopefully that makes sense. Again, if your trigonometry is rusty, go have a look at those videos. So basically we need to get a second derivative here of this thing here. So c dash dash t, when you take a derivative of that, it goes to 0. You take a derivative of sine here, it goes to plus cos, and there's already a minus out the front, so this will be equal to minus pi 365. So sine goes to plus cos, so it's like that. You keep the inside the same, pi t over 365, and then what you do is you multiply by the derivative of the inside. The derivative of the inside is this. Okay, so then when you tidy this up a bit, c dash dash t, that's going to equal what's that, minus 76 pi, I think, or yeah, what's 38 by 2? 76, yeah, and then you get pi squared. It's a bit of a messy question. 365 squared on the bottom, and then you have cosine 2 pi t over 365. Now what we do is we go and we put both of these t values in. So I'm kind of running out of room here, but I should still be able to get it in. I can just you show it for the examiner like this. So I'll put in the 5.336. You'd show yourself subbing it in then, of course, but I ran out of room, so I'm just going to do it here in the calculator. So let me pause the video. I'm going to put 5.336 in for t here and see what it gets. And of course, you want to make sure your calculator is in radian mode before you do this. So when I type that one in there, I get minus 5.60, kind of, doesn't really matter, 7 by 10 to the minus 3. All that matters is that this is negative, and that's less than 0. So that's actually the maximum point there. Okay, that's the max. That's not what we're looking for. So this must be the min here. So I'm going to go and put that one in here. So we go c dash dash 177.164, and hopefully this number is greater than 0. Let's check. So yeah, so I put that in there and it's good. It's basically the same number. This is usually what happens. It's the exact same number, but it's got a positive on it. See, it's a plus. And so because that's greater than 0, that is the minimum. Okay, so the first minimum occurs when t is this. And that's what we're after, the value of t. Okay. Yeah. So that's hopefully okay for people. And then if it asked you when does the next local Oh, it wanted the first local maximum. Sorry, I didn't read that properly. So that there is the first local maximum, of course. Grant, if it asked you for the next local maximum, that would be pretty tough, okay? So what you got to do is you got to move forward the period. And so you should know that there's a formula here where it's like this number here. It's like period equals 2 pi over c, where c is that number there in front of t. Again, if this is rusty, go have a look at those trigonometry videos. So if you sub 2 pi over 365 in here, you'll see that the period itself works out as 365. So if you wanted to advance from this point to the next point, you just add 365. It's probably the units of t are probably days. You add 365 to this. So the next local maximum would occur at 370.336 days. Okay, hopefully that makes sense to people. That was a pretty great question there, okay? So we'll move on to this one here. So we have a hemisphere, right? The volume of a hemisphere, so a half sphere, is increasing. So we have the formula for this. So when you read stuff like this, we should all know that the volume of a full sphere, we can have our, I probably need my formula tables up. Let me get it up here. Okay, so we're at the formula tables. So you should all be aware of formulas like this in your tables book. So for the volume of a full sphere, it's 4 over 3 pi r cubed. Pi r cubed. Now, if we're talking about a hemisphere, you obviously half it. So it's just going to be 2 pi. Okay. Now, this is one of these rates of change questions, right? So we got to read this carefully. And there's going to be a few of these in this PDF, and you're going to see that there's a kind of a specific way to do it. So focus in on what's happening here. The volume is followed by this formula. We're told that it's increasing at a rate of this. Now look at the units. The units tell us what this thing is. It's dV dt, okay, because it's volume per second. It's dV dt, and it's positive as well, so it's a 450 positive, okay? Right, and you got to watch out sometimes. Sometimes they're mean in a question where they like mess around with the units. This is in centimeters, and something else might be in meters or millimeters, but they haven't done that here, okay? They're being relatively nice. Okay, so that's dV dt. Now we continue reading. The rate at which the diameter, okay, so be careful, they talk about radius, now they're talking about the diameter x of the hemisphere is increasing with respect to time. Find, okay, so there's always, in these questions you're always asked for something, and that will be known as your question mark. So what we're asking for here, the rate at which the diameter x is increasing with respect to time. With respect to time, so that's with a dt on the bottom. So once you read the question and you identify what you're looking for, we know it's dx dt, we put a question mark beside it like that. So that reminds us what we're looking for, okay? And as you'll see in a second, we always pull the question mark apart, as you'll see in a moment. Give your answer in centimeters per second, okay? Remember the volume of a hemisphere is this. So where did they get that from? Where did they get that from? So we probably could have derived that ourselves, knowing that the radius is x over 2 if the diameter is x. So then r cubed would be x cubed over 8. And you put that in there, you'd get pi x cubed. The 2 would cancel with the 8 to give a 4, and then your 3 by your 4 give a 12. So you could have derived this formula yourself, but they were quite nice here this year, and they just gave you the formula. So V for volume is pi x cubed over 12. Okay. So they gave us that. We don't need this. Right. So there's always this pattern, right? There's always this pattern. You're always given something. There's always a formula, and there's always a question mark. And these, it's every time, it's the same pattern over and over again for these rates of change. So if you find rates of change questions hard, once you see this pattern, they shouldn't be hard, okay? So you're given a numerical value like this, there's a formula, and then there's a question mark, okay? You, first of all, always pull apart the question mark. So dx dt, you pull it apart using the chain rule. You draw two straight lines like this. Dx has to go here. The top thing has to go on the top left. This has to go on the bottom right. You then have, you can put whatever you want here. You can put the number 7 there if you want it, because the number 7 would cancel down and you go back to dx dt. So you have the ability to put whatever you want there. Now, it makes sense based on the question it talking about volumes V to put dV in here. So basically you get the thing you're looking for, the question mark, by getting these two things and multiplying them together. Okay? Right. Where are we going to get dV dt? Look, it was the thing given to us in the question. So all we need to get now is dx dV. What we can get pretty easily from this formula here is dV dx. We just take a derivative of this, and that'll work out as multiply down by the 3. It'll give a 4 on the bottom then, so it's just really pi x squared over 4. Which multiply down by the 3. I'm sure everyone's happy with that. Now, if we know dV dx, we can very easily write dx dV. You just flip both sides. So then it's 4 over pi x squared. Okay, so that's it. That's all you do. And that's it. That's your answer. So you just sub them in now. So dx dt, subbing the two things in here in the two brackets. So dx dv was this. It was 4 over pi x squared multiplied by dv dt, which was 450. And then basically they told us when x was 20 centimeters, and that matches the units of the question. So we should you'd sub it in neatly for the examiner, but I'll just do it quickly here. That was x squared, and I know that 20 squared is like 400. So that's 400. Okay, so let me type that into our calculator, and then we'll discuss what the units are. I think they gave the units in the question, which is a bit ridiculous. It's always a thing to make the student have to think about what the units are, you know. And then multiply by 450. And so this works out as, let me get red, when we type that in there, I ran out of room. This would be written underneath if I had room. So dx dt, when you multiply those together, you get to the nearest decimal 1.4. And the units, x is in centimeters, and t is in seconds. So this is 1.4 centimeters per second, and it's a positive number as well. So it's increasing because it's positive. Okay, so hopefully people are good with that. So make a flashcard on that pattern. You'll see more of these questions I know as the video goes on. You'll always be given something. There'll always be a formula, and there'll always be a question mark. And you always pull the question mark apart like this with two flat lines. Literally, it's that pattern every single time. Okay, so what are we on now? 27 minutes in the video. Okay, so I think, yeah, we're doing this one as well. So Kristen is some mountaineer. Okay, something hill about K2. One of the climbs to her. Base camp 5,000 meters. So you kind of see that some of this information is already in the thing. So the base camp is there. So you can see if we put T in as 0, we'll get that the height is 5,000. So that's them probably at base camp. Okay. So you can pause the video and give this a go, you know. Find the time it took her to reach the max altitude. So the maximum altitude. So we don't know what the max altitude is. So basically, we can work this out by maximizing a function. So the way you maximize a function is you get the derivative and set it equal to 0. So h dash t will be equal to, taking the derivative here, it'll just be 300 minus 30 t squared. I'm sure everyone can take that kind of a derivative. Constant goes to 0, that kind of thing. Set it equal to 0. I'll divide everything by 30. So then I'll get 10 minus t squared equals 0. Now you got to be very careful here. T squared equals 10, right? So t is technically equal to plus and minus 10, root 10, okay? But I don't think t can be negative. It's a mock paper. It should be a bit clearer that t can't be negative here. So we'll assume the positive answer. So t here is root 10. And t has units, of course. T is in hours. So it took her root 10 hours to climb here. And root 10 as a number, it's a little bit bigger than root 9, so it'll be a little bit bigger than 3. And so it's t here was 3.16 hours. Okay, cool. Moving along. So that's how you maximize a function. That's the max elevation there. So, and there was only one. Well, there were two turning points here, but there was only really one positive one, you know. So there was only one solution there. Calculate the max elevation. So to get the max elevation, we just put the time when max elevation occurs into our function for height. So we'll go and put root 10 in here, h root 10. It's 5,000 plus 300 multiplied by root 10 minus 10 times root 10 cubed. So I'll type that in here. 5,000 plus 300 root 10 minus 10 multiplied by root 10 cubed. Yes, okay. So it seems to be 5632 point, correct to the nearest meter. So you write it like this first, and then you just say it's 5632 meters. Okay. Yeah, so that doesn't seem to have gone, she doesn't seem to have gone much higher than that, you know. But yeah, that's the way, anyways, that's what the maths are saying. So it's only 600 meters, but 600 meters is quite a lot if you're going up very vertical peaks, I suppose. So we'll crack along. Find the rate of change. Find the rate of change in the elevation over time. So that's a little bit of a funny question there. So what that is, the rate of change in the elevation over time. So it's a mock exam. It's hard to know what to say there. That's not very specific. So for me, you know, H is elevation, and they ask for the rate of change of elevation. They're basically just asking for H dash T there. So again, it's basically 300 minus 10t squared. That's just what it is, you know. So I don't really understand what they're getting at there, you know. It doesn't sound like they want a second derivative. The rate of change, yeah, no. Okay. If they asked for like her vertical acceleration or something, that would be the second derivative. Okay. Use integration to find the average rate of change. Now, okay, so this makes a bit of sense here. So they want us to use integration to find the average rate of change of our elevation. So they really got us to just remind ourselves of this function here. So then we could use the way of averaging a function. Okay. So let's do this. So what we have, we should know. I think I talked about it in the previous videos on differentiation rules. So there's an average value function, and it's this. It's 1 over b minus a integral of the function. We'll call it f of x with respect to the x from a to b. Okay, and a and b are just the 2 points. Okay, so we know I'll need that number I had from a second ago. Hopefully my calculator hasn't got rid of it. Yeah, so we need to remember that 5, 6. Well, it's mainly the time. We need the time. So I think the time was root 10. It took her root 10 hours to get up to the top. And at 0 hours, she was at base camp. Okay, so they'll be important in a second. So that's basically going to be our A and B. They're going to be times. Right, so this here, we're asked to get the average value of this function, her average rate of change between the two places. So what we got to do is we got to integrate this function with respect to the two times, with respect to t, but then between these two times here. So again, if you don't know what the average value function is, or that's like a curveball, what I'm after writing for you there, you know, you need to go back to the textbook and have a revise of that. So it's 1 over b minus a, so these are going to be 2 times here, root 10 minus 0. And we're going to integrate from 0 to root 10. And then we're going to integrate, we're told we want to average this function, if you read it specifically, the question. So we want to average this function. Okay. So that's with respect to dt. So we're going to integrate that. We're not going to, we won't need to add a plus c here because this is a definitive integral. Okay, so what that'll work out as is average value equals 1 over root 10. We'll change this to a straight line because we can do the integration. And then when you do it here, it's basically 300t minus 10. Hope I took a derivative of that properly. You scroll up. Yeah, that's pretty embarrassing. So that should be 30 there. Okay. Yeah, because I remember earlier on, didn't we divide by 30 and got like a 10 there? Okay, so that's no harm. It's been fixed now, so you can relax. Okay, where am I here? Yeah, that looks good. So yeah, this here is 30 t cubed. Let me tidy this up. We're integrating this function here. So this is, and this here is obviously 30t squared. So then this becomes 30t cubed over 3. Okay. Looks good to me. Okay, and then what we do is we actually sub it in now. So to get this average value here, this is what we call average rate of change. Average rate of change, and so what that'll be is 1 over root 10, and then we put in the limits now. So we have a big square box out here, and then we put in the limits. So you put the root 10 in. So you go 300 root 10 minus, that's 30 over 3, so that turns into a 10, and then we have root 10 cubed. And the great thing is when we put the lower limit in, the lower limit's 0, so it's a bit just like 0 minus 0. Okay, so we'll type, actually it's pretty easy, type this in, you could even do it in your head, because you multiply in by the root 10, that just becomes the number 300. One of the root 10s cancel here. So then it's just root 10 squared, which is 10. So it's 10 by 10, so 100. So I can even do that in my head that it's 200 meters. Now it's not the units aren't 200 meters here. So it's average rate of change. So it's the average value of this function. So it's 200 meters per hour. Okay? Because the units of h dash t is dh dt, dh dt, and h was in meters and t was in hours from what I remember up here. This looks messy on the screen, so don't panic. T is in hours, yeah. So that is not 200 meters, that's 200 meters per hour, okay? That's our average rate of change. Okay. So hopefully people are okay with that. That was an interesting question, for sure, so I'm happy I done that there. So hopefully people understood that. Obviously make a flashcard on that that formula up there if you've never seen it before, average value function, and how you use it there, of course. Okay, great. So I'm going to scroll along here now to our next thing. So we're on 37 minutes for this video, so we'll keep moving. Okay, so I picked out this one here because they do like to ask questions on these cones. Okay, so you need to be familiar with I think I've one other one coming up in this PDF, but this kind of thing with the cones here and the similar triangles. So you gotta be sharp to that, okay? I think there's a question I picked out for that later. And of course that you can use kind of Pythagoras here when you're dealing with the cones, okay? Anyways, so pause the video, give them 2 parts a go, of course. And I'll snip them out here. We'll start working through them. Right, a company makes candles in the shape of a right circular cone. They give us the diagram. Each candle is made of wax, yada yada. As it fills, the melted wax is always in the shape of the cone. Fair enough. Okay, and R and H. Show that V, the volume of the cone, is such. Now you should know, you can go to your tables book, the volume of a cone like this is pi R squared H. You can just go to your form tables and find that. So what can we write from this here? We can sort of write, surely we're meant to know something here. Where did they get this from? Look at this here. This is what we're missing. They did not put this in the diagram. Its height is the same as its diameter. So the diameter is 2r. So that means h equals 2r. So you got to watch out for sneaky things like that. So then you just basically go 1 over 3 pi r squared times 2r, and then that gives 2 over 3 pi r cubed. Great. The volume of the cone of melted wax. Now this is it. This is a rate of change question, okay, people? So we're going to test out our thing from last time, see if the pattern is the same. They give us something. I don't even need to read what it is. I can tell what it is. It's volume per second, so I know it's dV dt they've given me. And they say it increases, so that's a positive 0.5. I just watch out for the units, centimeters, 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 so there's no trick with the units, so everything's fine. Okay, let's read what we're looking for. Find the rate at which the radius of the cone, radius, is melted wax increasing with respect to time. Radius, so I'm looking for d or dt, that is my question mark, And what do we need? We need a formula. Oh, lo and behold, there's the formula. And there are the three things again. What's the first thing we always do? We always take the thing that is the question mark and we pull it apart, two flat lines. The dr has to go here, the dt has to go here. Because we're talking about volumes, it makes sense to put the dv here. So we need two things. When we get two things, we have our answer for the examiner. dv dt, we have that. Lovely stuff. So we just need dr dv. Where would we get that? We'll get that from differentiating the formula. We can get dv dr from this. Pretty easy. And we'll get ourselves multiply down by the 3. So you see you'll get 2 or, because the 3 will cancel then, 2 pi r squared. And so then what we're actually after dr dv is just that flipped 1 over 2 pi r squared. So then subbing in here, dr dt will equal the two brackets, dr dv, the thing we just got there, 1 over 2 pi r squared, and then it's multiplied by dv dt, which is 0.5. And then we were told to get this when the radius is 4. So that's the number 16. You'd show that in another line though. And then give your answer in terms of pi. Fantastic. That's the way to give it. So then this here is 1 over 2 times 16. So that's 1 over 32. And this is 0.5, which is a half. So this is 1 over 64 pi. Hopefully you can see. What are the units? The units of dr is centimeters. The units of t is in seconds. So this has units of centimeters per second. Great stuff. Okay, so again, flashcard on the fact that there's three things, you know. Okay, that was nice and quick. That's fantastic. Into two-page format, and we'll scroll along now. We're on 41 minutes. The rabbits. The rabbit question. Okay, so this is it's mainly algebra stuff. Okay, it starts off with a bit of differentiation, and then it swivels into some algebra. So we'll snip this, and we'll bring the rabbit with us. Okay, so the population of rabbits P on an island in hundreds, that's the thing we might need to watch out for, is given by this formula. T is in years, and T is always greater than 0. This formula does not work if T is negative. Find the intervals when the population is increasing and decreasing. Right, you need to know something from your when you were going through the calculus and the differentiation, okay? When a function like this is increasing, its derivative is greater than 0, okay? So basically, if f of x is your function, when f dash x is greater than 0, a function is p of t, the original function, is increasing in value. Okay, and if you didn't know that, make a flashcard on it. And the same here, when p dash t, that when your derivative is less than 0, the original function p of t is decreasing in value. All right. So make a flashcard on that, and of course go back to the textbook to have a glance at that yourselves, you know. Okay, so that's kind of why I picked this question out here, to kind of remind students of that big thing, because they love to examine that, you know. Right, p dash t, let's work it out. So it's a bit annoying. You need to use a product rule for this. So u equals t squared, v equals ln 3t. Underneath it, du dt is 2t. Underneath this, dv dt. How do we take a derivative of a log, an ln? It's 1 over what's in there multiplied by the derivative of what's in there, which is 3. And so then that just works out as 1 over t. So then when we take the derivative of this, we just sub into our product rule. I'm sure everyone can use a product rule here. It's very straightforward. So it's u times dv dt, which was just 1 over t, remember? U was t squared. I nearly got caught there. U dv dt, yeah, plus v, which was ln 3t, and then that's multiplied by du dt, which was a 2t. Okay, so then this here works out as a t plus 2t ln 3t. Okay. So we're basically asking the question. I think I've done that correct now. I don't see any issues there. Always good to just pause for a second and kind of check, see if you see anything. No. So we're basically asking when is this function here increasing and decreasing in value, okay? So yeah, okay, I'm just going to pause now, make sure I have all the calculations done correct before I go hammering into this, okay? Okay, yeah, no, that's all good there. So let's get cracked into it. So we'll do the when it's increasing first. So as I said, when p dash t is greater than zero, we're looking at the increasing scenario. So let's work out when that happens. So we go t plus 2. So it's basically an algebra question from here out. So it's when is this thing greater than zero? Okay. So let's first of all kind of factorize it out a bit. So it's a little bit annoying. So that it's an inequality. So sometimes a good idea here is to kind of set it equal to zero, okay, for the moment, and see can you get some solutions. So let's do that. Let's factor out the t, and it leaves behind a 1 plus 2 ln 3t equals 0, right? So when is this thing 0? It's 0 when t is 0, and that's not one of our solutions because t is greater than 0, so that solutions are ruled out. So the other option for this being 0 is this in here. So we get a 1 plus 2 ln 3t equals 0. So what we do then is we bring the 1 over, divide by 2. So we then get ln 3t equals minus 1 over 2. And then we should know how to reverse out of a log. So this has base of e, and then this is the power. This will be, the power is always on its own when you're in log form. So then this will be e to the minus a half equals 3t when you reverse out of the log. So if that doesn't make sense, go have a look at the log chapter and how to move into logs and out of it. So then t here will equal e to the minus a half over 3. Now there's a neat way you can write that. E to the minus a half is e to the half on the bottom. So I can rewrite this here just for people so they can learn a bit of algebra here too. And anything to the power of a half is the square root. So the time when the derivative here, p dash t equals 0, that time is 1 over 3 root e. Okay, it's a nice neat number. So let's work that out as a decimaler just for the sake of it. 1 over 3 root e. And so after, this is the time when t is, so as I said, this isn't one of our solutions. So this function basically turns once, okay? It has one turning point, and that turning point happens when t is equal to 0.20, we'll say 2 years, okay? So because it turns once, right? Okay, if we think about a quadratic is something that turns once. So when you're coming from this side, on a U-shaped quadratic, you're decreasing, and then you go past the point, your turning point, and then you're increasing. If you're an N-shaped quadratic, you'll have your one turning point as well, but when you come from left to right, you're increasing, and when you come this side, you're decreasing. So this is a little bit of a tough question. The student would have picked up a ton of marks here for just getting this turning point value t. Now it's a little bit tricky to kind of work out. Let me clear some of these workings away. It's a little bit tricky to work out the interval of when it's increasing or decreasing. So I'll give you a hint to this. As I said, this function is going to turn once. So the way to do this is to test what p of t is, what the derivative is here, left and right of the turning point, okay? So basically get something like p dash 0.1 and then check a point after it, p dash 0.3, okay? So when I get, and this will make sense hopefully once I get the values. So we'll put that one there. I'll put this one here. So basically I'm going to put 0.1 into my p dash t here, which is in orange. 0.1 plus 2 times 0.1. So this was a tough question the year it came up, times 0.1. So it's actually good you see in a question like this being solved. So when I put 0.1 in, this is minus 0.1408. And when I put the 0.3 in, so you should be able to scroll across and change the number. 3 times 0.1, and I get a positive number. Now what does that mean? 6, 8. What does that mean? Remember what we said before. When p dash t is greater than 0, the function is increasing. So left of the turning point, the function is negative here, so it's decreasing. Yeah, so I'll just get this again. P dash t, when it's less than 0, you're decreasing. So you turn after 0.2 years. After 0.1 years, you can see p dash t is negative. So the rabbit population is decreasing before the turning point, and it's increasing after the turning point. So my answer to this question is the interval for when you're increasing. Let me get a good color for this. I'll use red. When we're increasing, when p dash t is greater than 0, that happens when t is greater than 0 but less than the turning point. No, I've got that wrong. So that's when it's decreasing. So actually, as we said there, when you're right of the turning point, you're increasing. So when p dash t is greater than 0, that's when t is greater than the turning point. Here, 0.2022. Okay, and then when we're decreasing, as we said, that's when you're left of the turning point, which was this here. Okay, so then that says where p dash t is less than 0, that's when t is less than the turning point. Okay, so basically before the 0.2 years passes, the rabbit population is decreasing. Very tough question. As I said, the student picks up a ton of marks for just finding the turning point, and then this is a bit tough to kind of get a point left and right of it and to judge whether it's increasing or decreasing before the turning point. Now, something that'll help here, I'm going to clear this away. I'm going to graph our rabbit population here in I'm going to graph the population here in Desmos, so give me a second. Okay, so I've typed this into Desmos. You can see I've called y, p, and x, t, so you can glance at that there. Let's make it full screen. So this is the function. So you can see, as we said, we're decreasing up to the turning point. See the turning point there, the 0.22. And then after the turning point, look at what's happened to the rabbit population. It's growing. Okay, so it's increasing, and it increases always after that. So as we said, there was only one turning point, and we worked that out. And so we just needed to get a value left and right of it to see if it's increasing or decreasing. Okay, and yeah, you could have just worked out. We worked out a kind of p dash. Like you can just basically get like 2 points over here. We subbed into p dash, but you could have subbed into p of t, and you could have just gotten 2 points left of the turning point and seeing are they progressively decreasing in value. And so that would have been another way to tell that this part was decreasing. You could have gotten a point here and here by going like p of 5, p of 6, something like that, or you can see that it's 0.5, 0.6, or whichever, because it's increasing. You'll see that it was always increasing after. Little bit of a tough question, that, absolutely. So don't be too upset if it was confusing, but make a flashcard on the important bits anyways, which was the finding the turning point and then getting a point left and right of it and seeing whether it's increasing or decreasing. And then obviously when the derivative is greater than 0, the function's increasing. And when it's less than 0, it's decreasing, the derivative. Okay, so yeah, hopefully people learned a good bit from that. So we have this question here from 2023, so we'll zoom in on this. Yeah. The rabbits, the tricky rabbit question. So what do we got here? We're told that we have some quadratic here, and it has this local minimum. Find b and c. Okay, so pause the video, give that a go. So hopefully you realize that they're talking about minimums, so the derivative is pretty useful here. So we get 2x plus b is the derivative. If we want to find the minimums ourselves, now this will have just one minimum because this is a U-shaped quadratic, so it just has one turning point. So yeah, if you want to find that turning point, you set the derivative equal to 0. So 2x will equal to minus b, so the turning point happens when x is minus b over 2. And because it says this is the turning point, then that's equal to 3. And then b is equal to minus 6. Happy days. And then the easiest way then to get the other point is to just go f of x, sub your newly found b in, is x squared minus 6x plus c. Just put the point into the function. So put 1 in for, minus 1 in for y, and put 3 in for x. So I'll do that over here in a different color. Minus 1 in for y and 3 in for x. So that's 9 minus 6 times 3 plus c. And then we get minus 1 equals 9 minus 18. That's minus 9 plus c. And so I'm seeing c is 8. Okay, so we just want to get b and c. And we got both of them. Great, sort of a bread and butter question. Now this isn't really differentiation, but it's a good limits question, you know. So I want you all to have a go at it. So pause the video and see, can you get it out? Okay, so when you're dealing with the limits question, you always see what happens if you just go and put the limit in. So if you put infinity in here for n, you're going to get like infinity over infinity. Infinity plus 1 is still infinity. So infinity over infinity, that's not 1. It's just what we call undefined. Okay, and that would be the same for this one. This one wouldn't be too bad, so we can actually evaluate what this one would be. The rule of indices here is that becomes like that. We should be all, you can go check your tables book if you don't believe me. 1 to the power of anything is just 1, so that's fine. And so we got 1 to the 3 to the n here. Now you can put infinity in there, and you get 1 to the 3 to the infinity. So that'll be 1 over infinity, and 1 over infinity is 0. So we know that this term is going to go to 0, but we don't know what this term is going to go, these two terms are going to go to. Right, so let's try and do that. So the method to do this here is you divide above and below by the highest power of n, but you want to show your workings here for the examiner. So I would go n over n plus 1 over n. You see how I just divided everything above and below by n? What you don't need to do it over here. What you can just do is simplify this as a single fraction. So split that one into two fractions. So it's n over n plus 1000 over n, and then, as we said, rewrite that other one as 1 over 3 to the n. Okay, so then this simplifies down to be, I need a different color so it doesn't look neat. This is 1 over 1 plus 1 over n plus 1 plus 1000 over n plus 1 over 3 to the n. So now that we've simplified that, we can go and we can work out the limit for that thing in green there. So the limit as n tends to infinity for this thing, you'd show your workings now because you can put it in here. So this will work out as 1 over 1 plus 1 over infinity plus 1 plus 1000 over infinity plus 1 over 3 to the infinity. And then your next line here would be shown for the examiner. That's 1 over 1 plus 0. 1 over infinity is 0. 1 over a huge, if you don't believe me, type into your calculator 1 over 10 million. You'll see the number is basically 0. Then type in 1 over 100 million, and you'll see it's 0. Okay. So, and again here, so 1000 over infinity is 0. And then 1 over, as we showed you ago, that is 1 over infinity as well, so that's also 0. And so I'm seeing 1 over 1 plus 1, so the answer is 2. Okay, cool. Nice little question. Right, into 2-page mode. So what's the video on now? It's on 58 minutes. Sure, we'll keep going. We'll maybe push a little bit past the hour. Okay, what do we got here? Yeah, so this is an important type of question people have to be comfortable with. They need to be able to get the, displacement, velocity, acceleration. Them questions come up. So there's one here kind of on it. A package is dropped from, say, a drone or an aircraft, and this is its velocity. Okay, it's got an exponential thing there. T is in seconds, and it doesn't say what v of t's units are. So there you go. That's a mock exam for you. Stupid mock. It didn't tell us the units of v, and then it starts mentioning it down here. So you'd have to mention it up here that v is in meters per second. Anyways, they're just so lazy, the people who write these mocks. So calculate the velocity to 1 decimal place of the package. Okay, so I'm sure everyone can just put 1 second in there and get a value. Okay, that's not hard. Calculate to 2 decimal places the time taken for it to reach a velocity of 15. Yes, so we will do that one. So this is the other way around. So they've given us v, and now we have to work back to t. So this is a bit of algebra for us to do. So give that a go, pause the video. So what you'll do here is you go 15 equals 75 times 1 minus e to the minus t over 10. So because that's one equation, one unknown, because our t is in the power, we're going to need logs. So we divide by 75, 15 divided by 75, that's 1 over 5. So we get 1 over 5 equals 1 minus e to the minus t. We're going to bring this guy over, the fifth over here, so that'll be e to the minus t over 10 equals 4/5, and we can use logs now. The base here is e, so the base will be the base, and the whole point of logs is to get the power on its own, so the minus 10 over t will, minus t over 10 will be on its own, and then that just leaves this slot then for the 4/5. And then what t will be, if you can move it around in your head there, it'll be you multiply by the 10 and then you multiply both sides by -1, so it'll be minus 10 ln 4/5. Hopefully people can do that sort of maneuvering. ln 4/5. So I'm seeing that that happens when t is equal to 2.23 seconds. Okay, you can just write s for seconds, but I'll write the full word seconds because my 2's look like they don't look like s's. It's the other way around. Okay, so yeah, that's fine. Find an expression for the acceleration. So we should all know that acceleration is dv dt. And if you want displacement, displacement would be the integral of v with respect to t, okay? And so if you had displacement, displacement would be then, if you had displacement and you wanted v, v would be equal to ds dt. Now you should know all of that, okay? So I'm just reminding you of this. I'm not going to go through it, but there are things you should know. So anyways, we're asked for acceleration here, so we got to know we got to take a derivative. So what we'll do first of all is we multiply out v of t. V of t is 75 minus 75 e to the minus t over 10. We'll take a derivative now. V dash t, we'll call it for a minute. We'll call it a of t in a second. Take a derivative of that, constant goes 0. So the number here does nothing. It's just going to be there. And then exponentials, when you take the derivatives, just stay the exact same. And then you just multiply by the derivative of the power, which will be minus 1 over 10. Now we'll call it a of t, because that's what v dash t is a of t. Okay, it's acceleration. So we multiply this out, the minuses will cancel there, so you get something like 75 over 10. What's 75 over 10? I'm not going to write it as 7.5, I think it's 15 over 2. It is. Fractions are better than decimals, okay? 15 over 2, positive, minus 10 e to the minus 10 over, minus t over 10. So you can see the acceleration is always positive, because this can never have a negative value. Show that as time goes on, the package will stop accelerating. Okay, so as time goes on, the package. So that's a pretty stupid question, because as time goes on, it will stop accelerating, but like you'll have to go to t equals infinity for that to happen. So this here is an exponential, right? I'll write it as the 7.5 so people can relax a bit. So it's e to the minus t over 10. Now, the 7.5 doesn't really do anything. What changes a is this thing here, because that's got a t in it. It can change value. So the graph of that, because that's exponential decay, looks like this. Right? So it looks like that. The idea here is that it will be an asymptote with the x-axis. And so what happens is, as t goes off to infinity, when t goes to infinity, then a of infinity will take on a value of 0. This is what exponential decay does. Okay, and if you don't believe me, you can test this. We can go and put in a big value of t. We'll put in like a equals 1,000 seconds. Okay, let's work that out in our calculator. It'll be just a little bit above 0. So this will be proof. Minus 1,000 over 10. So you see, it's just a little bit above 0. It's still positive. It's plus 2.79 by 10 to the power of minus 43. Like, that number is basically 0, okay? If you put 10,000 in, the calculator might even say 0. The calculator actually does say 0. If you put this in, it will say 0, okay? So yeah, so you believe me now on this exponential decay thing. So it's a bit of a stupid question. So basically, what I would do, that's actually enough for the examiner there. You just show that, and then you just do a times 10,000, and you go, it's even, you just say it's even closer to 0, okay? Your calculator actually says it's 0. And then you can do a to infinity, and then just say that actually is 0, okay? And then draw a graph. So it's not a bad question, but it's a bit silly all the same. Okay, so definitely that was a good one. Good learning for people there on their algebra and functions. So we're on an hour and 5 minutes now. How many more questions will I do? This looks like easy enough stuff here, so I will do this. And we're kind of, as you can see, the bar on the right there, we're kind of halfway through the document, so we're probably getting close to a good place to stop and then break the video into a part two, you know? Right. There's just two parts, yeah, because you see, you know they're linked because it's like 1 and 2, you know? So let's snip that. We'll go here. Okay. There's some function that if we get the derivative of it, we're probably going to need a quotient rule. F dash is this, show this, okay, and hence find the equation of the tangent at S, okay. Great, that shouldn't be an issue. So what people would do most of the time, they would use a quotient rule here, but if you've watched my previous video, I'm pretty much love using the product rule all the time by writing them like this. You can bring the bottom up like such, and then you can just use the product rule, U and V. So then you say U equals 2x plus 1. V is x minus 3 to the power of minus 1. Underneath this, you write du dx, and that's the number 2. Under this, you write dv dx. You multiply down by the power. You keep the inside exactly the same. You reduce the power by 1, and you multiply by the derivative of the inside, which is just 1. So then, and you could rewrite dv dx here. You can actually write that as minus 1 on top and an x minus 3 squared on the bottom. Okay, just reversing your indices. And same with this, you could write this as 1 over x to the minus 3 when you're subbing in. So then f dash of x, using your product rule formula from your tables book, which goes u. Everyone's used the product rule, I don't need to walk through it. U times dv dx, which is this thing here. So that's minus 1 over x minus 3 squared, plus v, which is this here, 1 over x minus 3, times du dx, which is 2. Right, so we could probably tidy that up now, 1 second. I'll use blue up here. F dash x equals, and there's a negative here, so I'll call this minus 2x minus 1 over x minus 3 squared. And then this is a plus a 2 over an x minus 3. We want to write them as a single fraction, so we multiply this one above and below by x minus 3. Putting a full bracket around that. So then our f dash x will have a single denominator of x minus 3 squared. This will have a 2x and then a minus 6. That plus 2x will cancel with this minus 2x, and our minus 6 will combine with our minus 1, give a minus 7. And that's it. And another thing, just to comment here, they haven't asked it in this question, but look at this, f dash x. You could be asked, explain why f dash x, explain why f of x is always decreasing, okay? It is always decreasing because, as we said, if a function is decreasing, its derivative is always less than 0. Its derivative is less than 0. So if its derivative is always negative, that's what less than 0 means, then this function is always decreasing in value. The y value is always getting smaller. And the reason it's always negative is because if you have x minus 3 squared on the bottom, that's something squared. It can never be anything other than positive or 0. It won't be 0. They'll say if this was a proper, they say it there. See, x can't be 3. So basically the bottom is always positive, the top is always negative, so then f dash x is always less than 0, so then this function is always decreasing. But they didn't ask that, so we won't go into it. They wanted the equation of the tangent at the point S, where x is 4. So we need to get a y value for that. So we get f of 4 up here to get the y value for this point. So we go 2 times 4 plus 1 over 4 minus 3. 9 on top and a 1 on the bottom, so that's a 9, and so the point is 4, 9, and the slope, we get the slope from subbing into f dash x, that gives us the slope of the tangent, so that's minus 7 over 4 minus 3 squared. Yes, so that's a 1 on the bottom, so that's the slope of minus 7, and then we use y minus y1 equals m times x minus x1. And we have a point and a slope now, so we can sub in. So we go y minus 9 equals our slope of minus 7 times x minus 4. Great. And did it give us a format? No, so we can just write it whichever way we like. We'll write it where everyone's brought to the one side, which is the more standard way, plus 28. So then we get a 7x plus y, bring a 28 over, 28 and 9, what's that going to give? 37? Yeah, let's gamble for 37. Okay. Right, the tangent at the point T on the graph is parallel to S. Find the coordinates T. So it says it's on the graph. So because it's parallel to T, it'll have the same slope. So that means this tangent also has a slope of -7. Okay. The tangent at the point T, did it mention a point T or are we meant to find a point T? Oh no, we're looking for the point T. Okay. On the graph is parallel to the tangent. Okay. At the point S. Right. Parallel to S. Let's find the equation at x equals 4. This seems confusing in terms of what they're asking. Let me pause and let me think about this. Okay, yeah, no, there is a way to do this. Okay, it's just a little unusual. So what we have here, we'll just kind of follow the instructions. So if they come up with a little bit of a funny one like this in the exam, you just follow what they tell you. We're told there's some other tangent that has a slope of -7. So this is our slope formula. So we just set our slope formula equal to -7. Okay, so we're just following the instructions. We're told that there's some other point on this graph that has a slope of -7. So let's see, can we get an x value for it? Okay, so now great thing is the -7's cancel. So then this will be a 1 over here. So then you get like a 1 equals 1 over x minus 3 squared. So we can multiply up by the denominator here. So let me make some room. So we get x minus 3 to be squared equals 1. So then we can square this out. We get x squared minus 6x plus 9 equals 1. I'll move up here because I ran out of room. We got x squared minus 6x plus 8 equals 0. You factorize this, you get x. I'd go that and that. Okay, I think that's our answers, yeah. Yeah, because they give a plus 8 and then they add 6. So our two x values where they're on this graph, there's a slope of -7 is when x is 4 and when x is 2. Oh, and that's great because we got this one 4. So the other point T here, so this was a great question. So it was a little bit of a head scratch, but you just kind of follow the instructions about the slope. So there's another point where the slope is -7 and that's when x is 2. Okay, and so we're asked for the coordinates of T, so we have its x value. Guess where we get its y value? By subbing in for y. So its y coordinate is 2 times 2 plus 1 over 2 minus 3. That is a 5 on top and a -1 on the bottom. So that's a -5. And so t as a point is 2 on an x and a -5 on a y. Happy days. So hopefully you got that out. It's a great question, that, to be fair. Okay, so video's on about an hour and 15 minutes now, and yeah, that looks like a great place to pick up the next part of this tutorial. Is this question here, which is on a rates of change question. So it's a very interesting one. This we will do this in the next part of this video. So thanks for watching, and we'll see you in the next video. Okay, so we're back for the part 2 of this video, which is on applications, questions that come up in past papers on differential calculus. Okay, so we said we pick up from here, so I'll get this set up for us. So what are we being told? So this is an interesting question. This is a rates of change question. It's interesting because it's related to a triangle here. So as we said, when we're given these rates of change questions, there's always 3 things we're trying to identify. So we're going to be given something. If we read the question here carefully, we're told that x is increasing, so it'll have a plus sign, at a rate of 4 meters per second. So you can tell what it is, meters per second. So that's per time, dt. And then meters is a displacement. So we should be okay, if we've done our textbook stuff, that s is the symbol for displacement, not speed. V is the symbol for speed, which we call velocity. Okay, so ds dt. Now what we could call it as well, we could call it dx dt. Okay, and that's probably not a bad name for it as well. So we can say how x is changing. dx dt is actually not a bad name for it. So it's a plus 4, and we can write meters per second if we want, but the units are kind of in meters per second. Okay, there's no tricks there. So this is the thing we're given. Then there's going to be something we're looking for. So if we read this carefully, find the rate at which BE is increasing. Okay, so that's an interesting one. So what that is kind of at the minute, it's like dBE dt. We'll write it like that for the minute, and we'll call it the question mark. We can come back to this in a second. And as well too, yeah, it's the distance dBE. So the two lines beside it means distance. And then what's the formula that will relate them? Well, you can nearly guess what the formula is. It'll be Pythagoras here. So this will be the distance, BE we could call it. Probably no harm giving it a name, but I'll call it BE like this for just for the second. So what does Pythagoras say here? What's actually, yeah, what I'll actually call this is, because it's not a nice thing to write that, I'll just write it D, but then you can tell the examiner it's equal to BE like this. Now D is not the best symbol in the world because, you know, we use it for our differentials here. So you got to kind of, when you're coming up with symbols like this, you need to pick good ones. So D doesn't really work there for distance. So you could call it H for hypotenuse. And I'll call it H for hypotenuse, even though it kind of means height, but it'll do. So then we're really looking for dH dt. Anyways, from Pythagoras here, h squared will equal x squared plus 7 squared. So then this is our formula. These are the three things. This is the thing we're given. This is the thing we're looking for, the question mark, and then this is the formula up here. Right. So as always, when we've got the three things identified, we take the thing that is the question mark and we pull that apart. So dH dt. We draw two flat lines like this. dH has to go here. dt has to go here, and it makes sense based on what's in this question to put dx here. Okay. So what we need now is we have dx dt, so we just need dh dx, right? So where do we get dh dx from? Well, we'll need a formula which is h in terms of x. So basically h here. So we're taking the square root of both sides. We'd normally go plus and minus, but h can't be negative, so we'll only take the plus solution here. So h is really just the square root of x squared plus, what's this, 49. And so h, because we have to take a derivative of it, it makes more sense to write it like with the half, like such. So then we can get dh dx here. It'll be multiplied down by the half. Keep the inside exactly the same. Chain rule basically. Reduce the power by 1. And multiply by the derivative of the inside, which is a 2x. Okay. So that's dh dx. And we're told we can just sub that in for the examiner. It's always a good practice that. And so this is this question solved basically. So like such, and then underneath it we're going to sub in. So the thing we're looking for, dH dt, is going to be equal to dH dx, which is this here. Now we can tidy this up a bit. So we have a half and a 2x. So this will be really just an x on top. And anything to the power of minus a half is just a square root on the bottom. So that's a square root x squared plus 49 on the bottom. So yeah. And then this is bracket 4, because that's the xt. And then we're told get this when the triangle is isosceles, so that just means this here is 7, because the two sides will be the same. So then we just put x in as 7, so we go 7 over square root of 49 plus 49 multiplied by 4. Okay, so I'll get a value for that in our calculator. So was it 7 by 4 on top and square root 49 plus 49. So that works out as, once I'd write it as 2 root 2 first, because that's what it comes out as. But then they want it into one decimal place, so 2.8. And the units of that, well, h is a distance, it's in meters, t is in seconds, so this you'd have to write meters per second, okay? Great, that's it. Hopefully you're seeing how easy these rates of change questions are when you understand you're looking for three things at the beginning to set up like this. And then your next step, you always know your next step, it's pull the question mark apart like that. These questions are so simple. Okay, so moving along here. So we've got that covered in reasonable time. I think this is another rate of change question. I think this might be one of our last rates of change questions. So obviously, as always, be pausing the video and giving these a go, you know, before I do them. So there's a particle that moves along a curve and it's y in terms of x, okay? And obviously if we to take a derivative of this, we'll be using our rules for logs, where we kind of bring, this is the square root, so it's all to the power of a half, it'll pop out the front, that kind of thing. Okay. In such a way that the x-coordinate is increasing. Now we've been told something here, so we need to be careful. In such a way that the x-coordinate is increasing at a rate of units per second. So that basically is dx dt, if you're happy with that. Dx dt there, we've just been told increasing as well, so it's a plus 0.4. And then this will be the question mark. Find the rate at which the y-coordinate is increasing. So then dy dt is a question mark here. Okay, and then obviously we have a formula then. So there's your three things. And then you don't panic once you've got the three things. You know what your next step is. It's pull the question mark apart, and then things become clearer. So this is what we're looking for. So we pull it apart. dy dt equals line, dy has to go there, dt has to go here. And so based on what we're talking about in the question, it makes sense to put a dx here. So we get these two things, multiply them together, and we have our answer. We already have dx dt, it's 0.4, so we get dy dx, and we'll get that by taking the derivative of this thing in pink. We'll rewrite that. So according to our rules of logs, all right, first of all, we'll write it as a 5x over an x minus 2 to the power of a half. We should know our rules of logs here, where the half can pop out the front. The power can just pop out the front like that, ln, not ln, ln 5x over x minus 2, and then we should know the rule that when they're dividing inside the log, that can turn into subtracting. So you'd have your half like this, with the big bracket, and then you go ln 5x, take away ln x minus 2, like such. And then it's pretty easy to take a derivative of this. You can just go, you can multiply in by the half if you want, but the half isn't doing anything, it's just a number. It'll be there at the very end, you know. So dy dx, the derivative of this is 1 over what's in there, multiply by the derivative of what's in there, which is 5, take away 1 over what's in there, multiply by the derivative of what's in there, which is the number 1. So then when you multiply in the half, see these 5's cancel here, so then it's 1 over 2x, take away a 1 over x minus 2. So that's your dy dx. So obviously we'll sub that in for the examiner. dy dt equals dy dx, which we got here, which is 1 over 2x minus 1 over x minus 2, and then times 0.4, and we were told when x is 2.5. So a new line, if you had room for it, I don't, so I'll just do my new line here as well. Put 2.5 in there for x in your next line. And you get an answer, and I'll get the answer for that now. So that's 1 over 2, it's 2.5, minus 1 over 2.5 minus 2, and then multiply all that by 0.4. If I've done that right, I'm getting that. So again, it's nicer write it as a fraction, unless you're explicitly told turn it into some decimal. So it's minus 18 over 25. And what would the units of that be? Y would be in units and T would be in seconds. So this is again units per sec, you could say seconds. Okay, cool. So why is that negative there? Find the rate at which this distance is increasing. Okay, so that's interesting. So I wouldn't have expected that to be negative, because it says the y-coordinate is increasing. So let me pause there and see if there's any issue with the sign or my multiplication. So 2 seconds. Yes, I see an issue. So when I multiplied in my half here, I didn't multiply it by this here. So there'll be a 2 here underneath there. And then same here. So when you type it in, then you'd have got a 2 multiplying this here. So I can just move across to my calculator. Update that. So that's nice. You had a kind of sanity check there. The answer shouldn't have been negative kind of thing, you know. So when I do that, I get still an updated answer now of minus 8 over 25. So that's still negative. So let me pause and have a think. Yeah, so I've had a careful look over my workings there. I can't see any issues. The answer absolutely is minus 8 over 25, and it is minus. And this question is incorrect in the sense that it says it should be increasing. The y-coordinate is not increasing, it's decreasing, okay, because we got a negative sign. And the reason why is because look at this, it's a mock paper, and they're pretty stupid for whoever writes them. Okay, so yeah, there we go. So that answer I gave you there is 100% correct. Okay, so let's keep moving along. Um, yep, we're looking for another star. So we're told find the range of values here for which f dash is negative. Okay, so and yeah, so that's tied into what's above here. So let's take a snip of our function so we can have it in front of us. And then we have our question down here. So find the range of values of x for which f dash x is negative. Right, so this is mainly an algebra question, so obviously pause the video and give it a go. This is something very important for your paper one. So the question starts off, first of all, in just getting a basic derivative, which I'm sure everyone can do. 6x squared minus 42x plus 40, right? Everyone can do that. Now, it says find the range of values for which this thing is negative. Now, we should remember from before, it's not tied to this question, but it should be something on our flashcard that when f dash x is negative, in other words, less than 0, um, it means the function is reducing in value, okay? So as in y will be reducing, okay? So that was something we mentioned before. Anyways, so what this is here, it's an algebra question from here out. 42x, you just follow the instruction. When it says is negative, it means less than 0. So we just gotta know how to solve. These are called a quadratic inequality. And if what I'm going to show you here doesn't make sense, go have a look at your algebra book on how these work. So what can I divide everything by here? Maybe I could divide by 2. So I get 3x squared minus 21x plus 20 is less than 0. You then try and factorize this. It usually will factorize pretty cleanly for you. So this is a 3x and an x. What would it be? 5 and 4 maybe? 5 and 4, no. 10 and 2. Let me think. So again, I'm going to pause here and just think of the factors. Yeah, so after looking at that for a moment, I'm not seeing that it's factorizing for me. Now, if you were panicked there, you just have a look back at the question and you see that there's this kind of hint that it mightn't factorize perfectly for you. So this corrected two decimal places thing is the kind of hint now that, okay, let's just check this in the minus b formula and see what's happening. So let's run this through the minus b formula, which I'm sure everyone can use. X equals minus b, so that's a 21 plus and minus the square root of, the sign doesn't matter here for the square, 21 squared minus 4 bracket AC all over 2 times a, so that's a 6. So then the two solutions work out as, I'll type these in here, should I take a second? 21 plus square root 21 squared minus 4 by 3 by 20 over 6. So yeah, they decided to go for a stupid question here where they have decimals on this. So we'll give them their two decimal places thing here. So x is 5.86, and then the other one is when you use the minus sign, and that gives us 1.14. Okay, so I don't know why they went for that, but anyways, so normally what would happen here is after you factorize this, right? After you factorize this, you'd get these two roots, but they're not actually your answers. You kind of write them off in the corner of a page. So what you do then is you draw a number line, and you draw 2 dots on the number line, and you plot the roots here on the number line. So whoever is the furthest left, so the 1.14 occurs first on a number line, and then you move over to 5.86. This here was a U-shaped quadratic, so you draw a U shape through these points. And then what are we to 0? Because we are less than 0, we shade the part of the curve that goes below the number line. And we just described that region there. That region is when x is less than 5.86 and it's greater than 1.14. So I done this question mainly so I could get people to remind themselves of that you need to know how to solve these quadratic inequalities kind of using this number line thing here. So to practice a few of them in the book if you don't know them. So they're important exam questions you should know. Okay, very unusual. They normally factorize, but there was a hint here that they weren't going to. So I'm suspicious that that they went for something like that, but they did. Okay, so find the coordinates of the stationary point. So I done this question here just so you understand that if for your flashcard, if you don't know what a stationary point is, that's just another word for turning point. So we know our cubics have 2 turning points, and they're called stationary points as well, okay? So just so we're aware on that. So doing this question then, it's a little unusual what's going on here. You have two functions, and then they're talking about another function h of x, which is the g of x put into the f of x, you know. Yeah, so let's get h of x first of all. So h of x will be equal to basically f of x with g of x put in for x. So this looks like ln 3x squared plus 1, okay? So in for this guy's x value, you actually put g of x. That's what that instruction means. Okay, so yeah, that's what that is. So then we're asked to get the stationary point, coordinates of the stationary point. So there must only be one. Okay, it didn't say plural there. So h dash x here, how do we take a derivative of a log? Well, it's very simple. It's just 1 over what's in there, multiplied by the derivative of what's in there, which should be a 6x. Yeah. Okay, and then when we want to find stationary points, we set that equal to 0. So, yeah, basically we have ourselves a situation here where we have a 6x over a 3x squared plus 1 equals 0. So you literally just multiply across by the bottom because nothing on the bottom could make this thing 0. So you really just get 6x equals 0. So that happens when x is 0. All right. So that's just the way this goes. And so we were asked for the coordinates, so we need a y value for this, and we get a y value by summing it into h of x here, put it 0 in. So then h of 0 will be ln 3 times 0 squared plus 1. And so it's really ln 1, and we should all know what the log of any number is 1, it's 0. So the coordinates of the stationary point here is actually 0, 0. It's just the way it goes. I might actually graph this so people can see it. I'll throw this into Desmos, what that function looks like. So give me a second, I'll clear this away. Oh, ladies and gentlemen, that is what that function looks like. And yeah, look at it. Look at it, turns once, and where does it turn? 0, 0. So the maths done it got the right answer, basically, yeah. So everyone's happy there. So we'll keep moving along. Nothing wrong with the answer being 0, 0, as you can see every now and again. So this is a good question here. So I've put an X beside this. So in the part 1 of this video, well actually in a previous thing on the channel where I done the differentiation rules, I talked about how the graphs of say y relate to dy dx and how that graph then relates to the second derivative. So I'll get that picture up here now. So let me pause the video and get it up. Okay, so there it is. This was shown in the previous differentiation video on the channel. So this is where I was teaching students about how the graph of, say, y relates to its derivatives graph and then to its second derivative graph. And see, this is really important. When the turning points happen up here, they are where its derivatives graph has a y value of 0. You see, they're the roots on this function. So in other words, they're where, as we know, when we find turning points, we set f dash x equal to 0. And that is why when this is a graph of f dash x, that's why its roots literally take on y values of 0 here, because that is where f dash x equals 0. And then the other important point is the point of inflection is where the second derivatives graph will have a 0 value on this. So I recommend going back looking at that video and then also looking at this in your textbook. But that graph there is really good. It's something worthwhile making a flashcard on. Great. So obviously pause the video, give this a go now that you know all this. So anyways, we'll do it. So 2022, this came up. The graph of a cubic function p of x is shown from 0 to 4. It is indeed. The maximum value of p dash x is in this domain. Oh, the maximum value of p dash x in this domain, okay, is 1. Right. That's interesting. So that's why they kind of give us up to here, okay? And p dash 0 equals minus 3. Okay, so they're kind of giving us some information there. That's actually a point on this graph. They say when we have p dash 0, so when x is 0, this thing is minus 3. So that actually is that is a point there, this sentence, where p dash is the derivative, of course. Use this information to draw p dash x on the second set of axes. Okay, so as I said to you, the examiner will be expecting this for you to do these dash lines down here, because the student is expected to know that these are the points where this will cross the x-axis here. And the derivative of a cubic will give a quadratic. And you were told that this guy's maximum value is a value of 1. And you can see the symmetry here. Okay, so what we're looking at is this, a quadratic like this. And that will be the full marks there. And this point actually lines up with the point of inflection here. Okay. And another thing as well too, I would have mentioned it previously in the video. This function is down on the right, and its derivative will also be down on the right. And that's to do with an algebra thing, which you should look up, where if the highest power of x is positive, the function is up on the right, and if the highest power of x is negative, the function is down on the right. So this is down on the right, so its cubic, sorry, might look something like minus 3x cubed plus 4x squared plus 5x plus 6, for example. The highest power of x here is x cubed. Look at its coefficient, it's negative, so that means it's meant to be down on the right. The derivative of this would be something like dy dx here. If we were to take a derivative of this, this would be like minus 6x squared plus 8x plus 5. But the point is, see how it kept the negative coefficient on its highest power of x, which is now x squared. So then this would be a sad face quadratic, as we know, when it's got the negative there. Okay, so good to have a revise of that. I have videos on that already on the channel if you want to look at the previous differentiation stuff. So that was a great question that year. It revised the thing I'd shown up for you there earlier. So let's keep scrolling along to our next X mark. We'll find another unique pass fails per question you're supposed to know. So I think this is the second type of question where because these are pretty important, the kind of displacement, velocity, acceleration style questions. So I think we already done one of them in the part one, so we'll do another one here. So I've marked probably most of this question out. Yeah. So we'll get stuck into this. You can obviously pause and try these parts as well after you've tried these parts. So pause and give those a go, and I'll just crack into them. These are very important. These can come up, and you need to be comfortable with your S, V, and A, and how they relate. You know, that V is ds dt, and so on and so forth. A is dv dt, that kind of thing. So revise that in your book if it doesn't make sense. Jack was driving along a road towards traffic lights. When he saw that the light was turning amber, he applied the brakes, and the car came to a stop just before the lights. The velocity, important now, the units are meters per second, after he applied the brakes is following this exponential formula, where t is the time after the brakes were applied. Great. Find the initial acceleration. So we need a formula for acceleration here. Acceleration is dv dt. Okay, so let's find A here. So dv dt, if we take the derivative of this, the 42 does nothing. Okay, so the 42 will just be there at the end. The derivative of an exponential stays exactly the same, minus t over 3. Nicer way to write it than minus a third t. And then what do we do here? We multiply, it stays exactly the same, and we multiply by the derivative of the power. And in the power is minus t over 3, and so its derivative is minus a third. And then the minus 15, because of the constant, just goes to 0. So that's dv dt there. And we can probably tidy that up. 42 and 3 do divide into one another evenly, so that's minus. So A is equal to a minus 14 e to the minus t over 3. So you see A is negative, and that should make sense to people because we're decelerating. Okay, so like a negative acceleration slows the car down. The word initial here means when t is 0. So then A, you can write it as function language here when t is equal to 0. Okay, that might be a bit messy for people. You could just write A of 0, or you could just write A and just put 0 in the examiner and know what you're on about. So you go minus 14 e basically to the power of 0. Anything to the power of 0 is 1, and so this works out as minus 14. Now you kind of are expected to know the units of this. So you can learn off what the units of acceleration are, or you can just make them up on the day. What are the units of the thing on top of A? A is dv dt, right? This thing is units of meters per second, as we were told here. This on the bottom has units of seconds, because that's dt. So what you could write here, and you still get your marks, it's meters per second, and the examiner will give you full marks for that. But it's better written as meters per second squared, okay? Because the s comes down here, and then it's two s's on the bottom. But again, don't worry, you can always work out the units by looking at what was in the derivative, okay? Great. The time taken for the car to come to a stop, right? So you've got to know that when the car comes to a stop, v is 0. That means the car is no longer moving when your velocity is 0. So basically we got to set v equal to 0 to solve part 2 down here. So when you set v to 0, you actually get a ton of marks for just knowing that. So that's why these questions are important. And if you're rusty with these, I recommend having a go at some of them in the book. So we set v to 0, and then what we do, we move this around, we get e to the minus t over 3 equals 15 over 42. 15 over 42. And then obviously t is in the power, so we're going to need logs here, aren't we? So then the base here is e, so the base of the log will also be e. The whole point of logs is to get the power on its own. And then that just leaves one slot here for the 15 over 42. And then we multiply both sides by minus 3 to get the, we bring the 3 up and just change the sign. I'm sure everyone can do that. So then it's really minus 3 log, we write log e as ln. So it's good to, you know, only need to pick up the calculator once if you're good at your algebra like that. So that's minus 3 ln 15 over 42. So the car comes to a stop after about 3.09 seconds, and that seems about right. Yeah, 3 seconds to bring the car to a stop. Okay. Great. You can actually work out what the initial speed was the car. Speed and velocity are pretty much the same. You can look up what the difference of velocity and speed are. Of course, the physics students will be fairly on top of that. So velocity is just speed with a direction. Okay, so like if you're traveling 10 meters per second south, that's a velocity because it's not just a speed, it's speed with a direction. But anyways, we're not going to get into that. You can work out your initial velocity here by just letting t be 0, and then this will become a 1. And so you can see the initial speed, initial velocity of the car is 42 minus 15, and that's 27 meters per second. And you can change that into kilometers per hour. You'll see it's pretty close to 100 kilometers per hour. And so that should, anyone who's doing their like driving theory test thing, so basically this car basically was going 100 kilometers per hour, and it was able to come to a complete stop in about 3.08 seconds or something like that we wrote there a second ago. So the numbers kind of match up to a real life case. Obtain an expression in terms of t for the displacement of the car after the brakes are applied. So we should know that displacement is equal to the integral of v with respect to t, okay? So we got to integrate this expression to get displacement. So the integral of 42 e to the minus t over 3 to the minus 15, and then don't forget your dt. Don't be the students that are going around now writing dt when you're integrating. So then s equals, the integral of this stays the exact same. The 42 doesn't do anything, it's just a number. And then instead of multiplying by the power's derivative, we divide by the power's derivative. So if you divide by minus a third, it's the same as multiplying by like minus 3. Hopefully people are okay with that. And then this becomes minus 15t. And don't forget your plus c. Okay. Yeah. And what you would have here is kind of an initial condition. You would say that s equals 0 when t equals 0. You can just set the problem like this, you know. So when s is 0, t is 0. So we'll just see if they've told us that. They'll usually tell you that in the question. But this is a mock exam, so they'd have been a bit clearer on this. So you set s equals 0 when t equals 0, just to kind of start off your displacement formula. Hopefully that makes sense to people. But they'd be clearer in a state exam to give you this instruction to find your c, you know. They always give you a point. So anyways, you set s is 0, and then you get 42. I'll change 42, I'll multiply in by the minus 3 now. 42 by 3. So you're getting minus 126 here. Minus 126, and then it's e to the power of 0. That's going to be a 1. And then this is a minus 15 times 0 because t is 0. And then you have your plus c here, plus c. So then we're seeing that c is equal to 126 because this is 126 times 1, and you bring it over, it comes plus to 126. So our expression for s is equal to minus 126 e to the minus t over 3 minus 15t plus 126. Okay, so that's your expression, and then that has units of meters. Nice to write meters afterwards, just to tell the examiner, you know, that formula is in meters, you know. Okay, so basically calculate the braking distance. So I need to kind of remember my time. Hopefully I can scroll up on the I can. It's here, yeah. So we got a time before of 3.09, and we were told to round it to 2 decimal places, so we'll use the answer from before. So it takes 3.09 seconds for this car to come to a complete stop, right? So we can work out the braking distance. for this. So we know that when we can just put this in and we can just see how long it took for the car to come to a stop. So S equal, and that's all this is, e to the minus 3.09 over 3 minus 15 times 3.09 plus 126, and we'll see what the braking distance was for the car. And I'm sure people can, if they're doing their driver theory test and whatnot, they'll know how many meters a car needs to have to stop at 100 kilometers per hour. Let's see, do we get a number here? That's reasonable. Minus 15 times 3.09 plus 126. So I'm seeing about 35 meters, so 34.67. And that sounds about right to me now. If a car is going 100 kilometers per hour on dry road, it might take 35 meters to stop. So this was a relatively good question. So it's very interesting. Okay, so yeah, that was nice. And that was good revision for people there and their displacement, velocity, acceleration stuff. Okay, so good. The video is on a half an hour now. We'll keep moving. This is all very important past paper questions you should know, of course. I picked this one out here because it's got another one of these calculus things. These come up quite a bit, so I've probably picked out two of these and a point of inflection thing here. So they're important past paper things you should know. So yeah, so I picked these out for a reason. So this is going to be an algebra thing again, so we'll do this. Right, so there's some formula up here. You can read the question if you want to learn more about it. Obviously pause the video, give it a go. But T is just followed by this function here. P is the number of digits recalled after T hours. So the person's probably forgetting things after time, okay? P dash T is always negative from this to this. What does this tell you about the proportion of digits? Right, it told us this, but we could have worked this out for ourselves. We can work out P dash T up here. The derivative here, what's this going to be? This just goes to 0. So then this is the minus 0.12, doesn't do anything. It's just a number out the front. The derivative of this is 1 over what's in there, multiplied by the derivative of what's in there. Derivative of t plus 1 is just 1. So the derivative works out as minus 0.12 over t plus 1, and t is always greater than 0, so then this thing is always negative. So we could have worked that out for ourselves, that it was always negative. Anyways, what does this tell you about the proportion of digits? So because it's always negative, it means that the person is always, P of t is always reducing in value. If the derivative is negative, it means the y value, the P of t, is always, it's always reducing in value. And what does that mean in terms of the context of the question? It means the student, as time goes on, is always forgetting more digits. So that you'd write that out. I'm not going to write that on the Zoom here, but it means from an algebra point of view, P of t is always reducing in value. And in terms of the question, it means the student then is always forgetting more digits as time goes on. Great. Use calculus to show that the graph has no points of inflection. So we should know, if you want to find a point of inflection, the way you find them is you get your second derivative, which would be p dash dash t here, and set it equal to 0. And this is how you find points of inflections. Now we remember from a second ago there, p dash t was equal to minus 0.12 over t plus 1. So we just got to take a derivative of this. That the pluses and the t's look the same. That's disastrous. Okay, over t plus 1. I better tidy that up. We can write that better. T plus 1. So you don't need a quotient rule for this. The reason you don't need a quotient rule is because it's just a number on top. So what you can do is you can rewrite your p dash t here as minus 0.12. You can bring the bottom up and say it's to the power of minus 1. You can take your derivative like this. You can go p dash t equals, this is just a number, it does nothing. So you multiply down with the power. So that will become a plus 0.12. The inside stays exactly the same. You reduce the power by 1, and then you multiply by the derivative of the inside. Derivative of t plus 1 is 1. So there will be your workings for the examiner. And so then p dash dash t, as it's called, p dash dash t is equal to 0.12 over, when you have a minus 2, it's the same as being squared as on the bottom. And then, as we said, we set that equal to 0 when we're looking for points of inflection. And look at this here. there's no way the bottom can make the thing 0, so you just kind of multiply across it, and your algebra step would say that 0.12 equals 0, but you would just say to the examiner, but 0.12 can never equal 0, therefore no solutions can be found, and therefore 3 dots means therefore no points of inflection occur. Okay, great. Good revision for people, how that works out. So we keep moving. So this was from a deferred exam here. So this is just kind of bread and butter stuff. So we want to get a minimum, maximum, and a point of inflection. So pause the video and give that a go. Great, so hopefully you gave a go at that. So yeah, I'll just hammer that out here. So what we need is the derivatives, obviously. F dash x is 3x squared minus 12x, there's no plus 3. And then we'll need the second derivative as well to test who's a max or a min. So we'll just work it out here because we'll need it as well for points of inflection. So that'll be 6x minus 12. All right. So if we want to find the turning points, we set f dash x equal to 0. And so then what do we have? We can divide by 3 and we get x squared minus 4x equals 0. You do not divide both sides by x here. The way you solve this is you factor out the x. See? And so the two solutions are when x is 0 and when x are 4. Now we need to get y values for them, so we sub them back in here. As you can see clearly, when x is 0, y is 3, so you can just write 0, 3. It's pretty obvious. You'd show the workings for that though in your state exam. When you put 4 in here for x, what's that going to give? I can sub that in here. Obviously you need to show the workings for this. The way you'd show this for the examiner, you'd go f of 4 is equal to 4 cubed minus 6 times 4 squared plus 3. 4 cubed minus 6 multiplied by 16 plus 3. So I got minus 29 for that. So you just show it for your examiner like this. F of 4 is minus 29. So then the point is 4 minus 29. So we don't know who's who though. We don't know who's the max or the min, you know. So the way we test them is with the second derivative test. If f dash dash x is greater than 0, it's a little counterintuitive. If you're greater than 0, you're a min. And if f dash dash x is less than 0, that's a max. So let's test these out. So let's go f dash dash this guy's x value, which is 0. When you put 0 in there, you get minus 12. Minus 12 is less than 0, so that's the max. So this guy is the max point. And then if we go f dash dash this guy's x value, which is 4, you can see that's 24 minus 12, so that's a plus 12. They're usually always the same value, but opposite sign, so that's greater than 0, so that's the min. The local, and that's the local min. Okay, and then the point of inflection is got by setting this guy then equal to 0, so you just do that separately for the examiner. F dash dash x equals 0, so then that's 6x minus 12 equals 0, so then x is 2, and then we need a y value for that, so you go f of 2 equals 2 squared, which is 8, 2 cubed, which is 8, minus 6 by 4. You'd show more of the workings though, obviously. 6 by 4, 24, plus 3. So that's a minus 16, probably minus 13, is it? Ah, yeah, whatever. 2 minus 13. You'll type it into calculator, you'll get it correct anyways. Okay, so there's, and just say what that is. That there is the inflect. The examiner will know what it means. Okay, cool. Very important. Obviously, everyone can do that kind of a question, hopefully. So just in case there was anyone watching that couldn't, that's why we put a dash there, you know, because you're supposed to know that, of course. It's really important. Now, I hope everyone knows what inverse means, what an inverse function looks like. So this is mainly an algebra thing. It's not so much differentiation. So I'm just going to give you the quick rundown on inverses because I'm sure there's loads who don't know what they mean. So inverses are very much related to this line here. It's the 45-degree line. Now this was a real troll question this year, right? The 45-degree line is supposed to go through like 1, 1, 2, 2, and it goes up at 45 degrees. This is not going up at 45 degrees. Why? Because they were trolling this year and they made the x-axis go with a different scale to the y-axis. But anyways, normally this is a 45-degree line. And what happens is the inverse of a function always gets mirrored through it. So let's say this was the original function here in green, then its inverse would get mirrored through it and it would come out like this. Okay? So if that was a quadratic, the quadratic's inverse would look like this C. Now, you should know, if you don't know this, go revise it in the book. There's something called a vertical line test. And if you draw a vertical line and you hit a function more than once, it's not a function. So this green thing is not a function. So you can't get an inverse of this quadratic because when you draw a vertical line, you hit the graph twice. If we look at the original black cubic that's on the screen, is this a function? It absolutely is. Look at all my vertical lines. Every time I draw a vertical line, how many times do I hit the function? I only ever hit it once. So that is absolutely a function, that black thing. Now let's mirror this. Very tricky thing to do. We're trying to mirror this through the pink line. So this line here, when it gets mirrored, might curl off like this. This might curl this way. If that goes up to 6, this will mirror down to -6 down like this. So it's very tricky. If you're good at your art, you'll be able to do this. So you want to come maybe like that and then curl around to there maybe. So that's my attempt at drawing what the black curve would look like if it looked in the mirror and the pink thing was the mirror and it mirrored it out here. So the main issue here is that look at what's going wrong here. It looks like if I draw a vertical line, I'm going to hit it twice there, okay? So that's the main reason there. I'd say it's the fact that when you could explain this as well to the examiner, that if you mirror this and you draw a vertical line here, you're going to hit it twice around the 2 value there where there looks like to be an issue. Okay, and the technical definition for when you can get an inverse, it usually has to be see how it's related in your book to bijective, okay, being both injective and surjective, okay. Great. Let me see any other comments on that. No, I think that's okay. Let me clear that away and see if there's anything other comments to make. Yeah, just another comment as well too on this. So another way to know that there wouldn't be another clearer explanation of this as well would be, as you can see here, this y value of 4, right? If you draw a line across, there's 2 ways you can get a y value of 4. See how it's this x value. There's actually 3. Let's just see this here. So there's multiple places where you can hit this and get, say, a y value of 4. So that's an issue then when you invert the function, because what will happen is x and y switches. So basically, if you have like multiple scenarios like this where you can get the same y value, that'll mean multiple y values can get the same x. So that's the vertical line issue. So when you draw a vertical line, you want to just hit the graph once. So it's like 1x to 1y. So that's another. So that would be a big issue when that gets inverted. Let me see, can I draw a clearer thing of this on Desmos? It'll be more useful for students. Okay, so I'm back. So I have a few more comments to add to this one. So I've done a pretty bad job at sketching an inverse for that. It's pretty tough to do it. It was really tough to do it because of the axis and stuff. So I don't use some software to kind of work back to what this guy's function was. So you see I've drawn it on a bit more of a normal x and y axis. Everything's a bit better scaled. So this is the 45-degree line I'm on about, the y equals x line. And so there's our original function drawn properly to scale. And you can see what the mirror of it looks like. And you can see, look at the issue. If you do a vertical line here, up at around 4, remember we were seeing there was an issue at around 2 when we drawn our sketch over here. But the point is, when you get its inverse here, you draw a vertical line, you're going to hit it more than once. So then that green thing is not a function, okay? And that will be good enough for the examiner. So the hint that there was going to be an issue here at 4 particularly is because, look, as I was saying to you there, if I draw a horizontal line here at 4, for just the y value of 4, I'm getting multiple x hits. Okay, there's 3 x values that can do that. And so when you invert the thing, if you've hit it more than once here, that's going to mean the vertical line test is going to fail here. Okay, so if a horizontal line hits it more than once, if it hits a function more than once, when you invert it, the vertical line will hit it more than once. And then if the vertical line hits it more than once, the inverse is not a function. Okay, there is no inverse. It doesn't exist. Okay, it's not a function. So that's a good revision there for people on functions, and then it just shows how tricky it is draw inverses of things when things aren't to scale like this. That 45-degree line is a bit confusing. Um, okay, so that diagram hopefully helped people a lot that I done up in the software. This thing here. Okay, right, we'll keep moving along. That was a good question. I hope people learned from that and they can make a flashcard or two on that, because you never know. This year, your exam could be one that has something on inverses and sketches, and that could help someone and they pick up marks that they mightn't have otherwise. Um, and that horizontal line, vertical line test stuff I showed you there. So let me go into two-page view here. Oh, of course, the minute I go into two-page view, the next question appears. So I picked this one out here because this has that similar triangle thing here, and we want to make sure students are prepared for this. It comes up quite a bit. So um, what you can have here is like water or sand or something in these right angular cones, and you can write a similar triangle relation from them. So basically you can always sketch kind of like a big triangle and a small triangle here. Okay. So, and it's good to have them clearly bigger and smaller. I could have even made this one a bit bigger, that kind of thing. So this here is 4 on the big triangle, and then this is 12 here. And then this is what we call R, and this is H. And so you can write a ratio here, okay? You can write big over small. You can write big over small. So let me get the correct way to write this ratio here. That'll be useful because we want H in terms of R. So let me think about this. This is easy though. Yes. So it's the ratio that the big triangle side to the small triangle side, 12 over H, will be equal to this side on the big triangle over its smaller side. So that's 4 over R, like such. So then you can get that H when we'll cross multiply first of all. So we get 12R equals 4H. We'll divide by 3. 3R equals H. And that looks about right. Yeah, 3 times the radius looks about the H here. So then that's what they wanted, write H in terms of R. Okay, so H is 3R. And that came from the similar triangle thing we done there. So just be good to revise that in your geometry textbook, a few questions like that with the triangles. But yeah, good to be prepared for that. Okay. So H is equal to 3R, and we'll need that for the next question here. H equals 3R. So the sand drains. Oh, this is a rates of change question. You can tell straight away by them giving us something. So we'll hammer this out. I thought we had done all the rates of change questions. The sand drains from the funnel at a rate of this. Now look at that. That's a volume per second. Okay. So that's a dV dt. Now it drains from this. So I'd actually say that that's like a negative. Okay, because it's draining. The volume is reducing. So the negative might be important, but we'll just put it in as a positive first. So it might be implied in the question that everything is losing sand, Grand. Now, is there any tricks? You always got to watch out for tricks with the units. Everything seems to be in centimeters, so there's no like switch to millimeters thing, so everything's fine. You don't need to go putting units in. Let's see, can we work out what we're looking for, the question mark. Find the rate at which the radius of the remaining sand is decreasing. Okay, so I would call that d or dt. And that's our question mark. And can we get a formula for this? Yeah, there's a few formulas we can put together here. So we have this up here, but that's not our main formula. We want something with volume. And this is the volume of a right angled cone. And you can look that up in your tables book. It's pi r squared h. And we know that we can replace the height of the sand here with 3r. So then v is always equal to, that's 1 over 3. Pi over 3 r squared times 3r, and that's nice because that'll cancel with this 3 here, and so then v then will just equal pi, and it's called capital R as well when we put the small r in as the radius, r cubed. So from that, just without thinking, we can write what dv dr is. Okay, we'll probably use this later, but we can just write it now. It'll be 3 pi capital R squared. Okay, anyways, what should we always do once we've identified the formula, the question mark, and what's given? We should always pull apart our question mark. So our dr, it's capital R as well, dr dt equals, we pull it apart, so I picked a bad color for this, but sure, we'll keep going. Dr has to go here, dt has to go here. It makes sense to put the dv here. And look, once we get these two things and multiply them together, we have our answer. Do we already have dv dt? We do. Can we get dr dv? Well, we have dv dr, so we can just flip this and get dr dv. So this then, when we sub in, is really 1 over 3 pi r squared multiplied by this number here, which is 3. Now, that there works out as 1 over pi r squared because the 3's cancel. Now, the issue is here they don't give us the radius, but they give us something to find the radius. You can see here they said that how much it's decreasing by, yeah. So because it's decreasing, that it's all implied in the question that the minus is, so we didn't have to put a minus in here. It's kind of implied in the question. Anyways, they give us a volume and we can work back to a radius from this. So they've basically given us the volume here is 8 pi, and we can work out what the radius is when the volume is 8 pi. So they sometimes do this in the questions, so it's good you've seen an example of this. Pi's cancel, and what must r be? R must be 2 for you to get an 8 from 2 cubed. So if r is 2, you put 2 in here, and so then this works out as 1 over 4 pi, because 2 squared is 4. And then that has units of centimeters, because r is in centimeters per second. Okay. And then, yeah, you can you can type it into calculator, whatever it becomes. Okay, 1 over 4 pi. I'll just call it out for people here that done this question. 0.08. Give it in centimeters cubed per second. Oh, give your answer in. Find the rate at which the radius is decreasing. Oh, is this a mock? I'll be very surprised if that's a state exam. So it's a deferred thing. So I'm reading this here. I wonder, is it a mistake? So they say to give your answer in centimeters cubed per second, but they've asked us to find the rate at which the radius of the remaining sand is decreasing. So the radius decreasing is in units of centimeters per second, and so they're on about centimeters cubed per second. So there looks like to be a bit of an error there in what they've asked and what units they think the answer should be in. So yeah. Anyways, the answer there for d or dt, which is what they say they want, is 1 over 4 pi, and that works out as 0.08 basically centimeters per second. Great, we'll keep moving. We'll keep moving. So we're on 53 minutes, not too bad, not too bad. So we have a question here. So we've kind of covered quite a lot of the applications that come up. So as this document goes down now, we won't have that many red stars because we've already done quite a bit, you know. Show that this curve has no turning points and no points of inflection. So we've already done a question a bit like this, so we'll do it again because they're really important application questions. So what we do here is we take derivatives, and you should know that derivatives of this are fairly easy because there's just a number on top. It's not another algebra expression. So what you do here is you just rewrite the function like such, where you bring the bottom up to the -1. Then you can take your derivative, dy dx, you multiply down by the power, -5, you keep the inside exactly the same, reduce the power by 1, multiply by the derivative of the inside there is -1. And so that tidies up to be a +5 on top, and you bring the power -2 on the bottom, and it's the same as being squared. Okay, now how can we show that this has no turning point? We then set this equal to 0 to find the turning points, and then we get 5 equals 0 when we multiply across the bottom. And then you just say, therefore, no solutions, and therefore, no turning points, okay? Great. So then we'll get our second derivative, which is called d2y dx squared. For that, what we'll do is we'll take a derivative of this. So think about this, it's really just a +5 out in front. Let me tidy that up. We want it in this format if we're going to take in derivatives. So then we with the 5 does nothing, so the 5 will just be there. So the -2, when it multiplies down, will hit it, so it's -10. The inside stays exactly the same, and we reduce the power by 1, and then we multiply by the derivative of the inside, which is -1. So yeah, that will be equal to 10 over 2 minus x cubed. And again, we'll set that equal to 0 to try and find a point of inflection. You set the derivative equal to the second derivative equal to 0 if you try and find a point of inflection. You get 10 equals 0, And then basically, therefore, there's no solutions to that. 10 can't be 0, you know? Therefore, no solutions. And then, therefore, no P of inflection, points of inflection. You'd spell it out clearer for the examiner if it was your state exam. No P of inflect, no points of inflection. Okay, that's a really bread and butter sort of thing. That's why I done it again, just so students know how to do it. John states that the function is always increasing. Is John correct? So if functions are increasing, their derivatives, I'm in the old form, its derivative dy dx or f dash x is always greater than 0. If dy dx is greater than 0, y is increasing. So we have to get dy dx here and show that it's always increasing. So we worked out dy dx there a second ago. I rubbed it off. I think I can remember it. I think it was something like a plus 5 over 2 minus x squared. Okay. So why is this always increasing? Why is this always greater than 0? So you just need to explain it to the examiner. You'll say that the top is something like 5 and 5 is greater than 0. You would talk about the bottom. The bottom is something that's being squared, okay? It's something squared. And then you could say which is therefore greater than 0. And then you would just say as top greater than 0 and the bot greater than 0, therefore it is always greater than 0. In other words, if the top is always positive and the bottom is always positive, then the number itself is always positive, and therefore dy dx is always greater than 0. So the function always increases. So obviously you'll explain that in much clearer, neater words if it was your state exam, but you have my voice, and my voice is kind of telling you what to write down there as well on top of my shorthand writings there, okay? Great. So what do we got here? Yeah, this is a nice question with a bit of trigonometry stuff here. So let's take a snip of this. So obviously pause the video and give it a go yourselves, and we'll crack into it here. So the diagram below shows t, which is a tangent to this, and it is a sine function. Sine starts on its midway line here. If you've watched, you're going to have a look at them trigonometry videos on the YouTube channel, and you'll learn a bit from them on how we can identify that this is a sine. And we know its period as well too. We should know it has a period there of pi, because period equals 2 pi over c. C is the number here in front of the x, so the c there, and the c here is 2. And so 2 pi over 2, so the period is pi. So that's why I put a pi there. Anyways, we might need that. So the diagram shows this tangent t, and it meets the function. It has an x value of pi over 6. We don't know what its y value is yet. Okay, but we could work out its y value fairly easy by putting pi over 6 into the function, which basically will tell us what the y value is on the sine function there. And then we're told k is where it crosses the y-axis. So what we need here, people, is we need to get this point. We then need to get the slope of the tangent, which will be take the derivative of the sine function here and get the value of the derivative at this point. And then we have the slope and a point on t, and then we can create t's equation, and then we can find where t crosses the y-axis by setting x equal to 0. Great, that's the plan. So we'll get straight into it. So hopefully that all made sense. So we'll get that point there. Obviously we know the x value is pi over 6, so we want to get the y value, so we sub in here h of pi over 6 is equal to 2 sine and 2 pi over 6, so that'll be pi over 3. And pi over 3, if I have a feeling this is just going to work out as root 3. I'll type it in though, make sure that calculator is in radians. 2 sine pi over 3. Yeah, it is root 3, because I knew this was root 3 over 2, you know, that's one of them good to know off by heart. So then that point there, let me make it nice and clear. That point there is pi over 6 comma root 3. So now we just need the slope of t, and we get that by going h dash x. This is a formula for the slope of the tangent everywhere on this function. So you take a derivative of a sine, it becomes positive cos. The 2 out the front does nothing. Just chills there before and after. And then you multiply by the derivative of the inside here, which is 2. So this guy, h dash x, as you should all know, is 4 cos 2x. Now we want to get, this is a formula for slope of the tangent. We're interested in the slope of the tangent to h of x at the point pi over 6, next value. So you want to tell the examiner that's what you're doing here. So you go pi over 6, and then that's 4 cosine pi over 3, because 2 times pi over 6 is pi over 3. And I know that to be 2, because I know this is a half in my head. So 4 cosine pi over 3, and indeed it is, it's 4 times a half, which is 2. So that's the slope. That's the slope of t. Now we have its slope and we have its point. We can use y minus y1 equals m times x minus x1. So then we go y minus root 3 equals m, which is 2, times x minus x1, which is pi over 6. Now we can spend a bit of time tidying this up if we want. But ultimately, yeah, I better do it. I don't want to panic people. So equals 2x minus pi over 3. And then what we can do then is we can write this in the y equals mx plus c format. So then y is equal to 2x minus pi over 3 plus root 3. And so because that's in the format of y equals mx plus c, c is where you intercept the y-axis from junior cert. And it's also when, if you put x in as 0, you see that this part disappears anyway. So it's another way of saying that basically this thing here is k. Because that's the plus c. That's what's adding to your mx here. The m is 2. So k there is root 3 minus pi over root 3 minus pi over 3. And it wants it to 2 decimal places. So I'll do that for people who've done this question. Minus pi over 3. And I'm getting about 0.8. K is equal to 0.68. Okay, cool. We'll move along. Good question, good question. Hopefully people learned from that. And yeah, say this was just another line. Say it was like something like 2x minus 3y plus 7 equals 0. The way you would find where it crosses the y-axis is you would just set x equal to 0, because that's how you get the y-intercept. You set x to 0, and then you move it around and get y. Okay, but that was easy in this question because we wrote it in y equals mx plus c, and you can just see c is where you cross the y-axis. Okay, hopefully that makes sense to people. It should. Okay. So we'll go into 2-page format and we'll scroll along. So I have something here. Now this is just another rates of change question. Now I've done so many of these that I probably won't. I'll just, you can try this yourselves. I'm just going to identify the 3 things for you, just to show how simple these questions are. We've done so many of them. A sugar cube dissolves, the volume decreases at this rate. Look at the units. It's volume per second. So that's dV dt equals 1 over 20. That's the given. We're told it's a sugar cube, right? A cube is really straightforward. If one of its sides, the side length is x, its volume is x cubed, okay, because it has all dimensions the same. So that's our formula. And now we need our question mark. Find the rate at change of x. So they're really asking for dx dt. So that's equals question mark. So again, there you go. And then how would this question proceed? You just pull dx dt apart, like we've been doing before. So these rate of change questions are so simple once you identify the 3 things, and it gives you a direction, then you know to always pull the question mark apart. And it makes sense to put dv in here. And there's your dv dt, and multiply it by dx dv. dv dt is 1 over 20. dx dv will come from here. dv dx is equal to 3x squared. So dx dv will be 1 over 3x squared. And so you just need a value for x then. I'll just sub this in here because the question's basically done. 3x squared multiply with this thing, which is 1 over 20. This looks messy, but you see, I just don't care because we've done loads of these, you know. So they give us the volume, but that's enough information for us to work back to x. So if the volume is 1 over 64, we just sub that into v equals x cubed. And you can see then that you take a cubed root to the other side, x is 1 over 4. Okay, so basically then our answer here is 1 over 3 bracket 1 over 4 squared multiplied by 1 over 20. And that'll just work out in your calculator in units of cm per second, because x is in centimeters, t is in time. So that'll be centimeters per second. You can just type into your calculator whatever. 1 over 3 times 1 over 16 multiplied by 1 over 20. Great. Yeah, and obviously that, yeah, it's okay. Everyone gets it, I hope. Those rates of change questions are easy once you identify the three things like we've been teaching you so far in the applications questions, and also yeah, in the videos. Okay, keep scrolling along here. We're nearly at the end of the document. Good thing too, the video's on about an hour and 5 minutes there. So I have another question marked here with stars. Let's have a look. Use the function, it's an exponential, to find the average number of bacteria in the colony from this to this. Right? Pause the video and give a go at this. You should know what this needs. So that's a big buzzword there, average number. And they give you a function. They want the average value of a function. Average value. And we should know the average value formula is an integration. We use 1 over b minus a, integral from a to b of the function with respect to whatever the variable is. So it's going to be t here. So to get the average value for this thing here, we got to integrate from 3 to 12. So that tells us our b and a. It's 12 minus 3. Okay, and we're going to integrate from 3 to 12 of this function here, which is 450 e to the minus 0.065t and then dt. Okay, so what's this going to work out as? The average value will be 1 over 9. We can integrate this, so I'll change this to a straight line now, like such. And then what we do, the 450 does nothing. When you integrate this, an exponential stays exactly the same. And then instead of multiplying by the derivative, you divide by the derivative of the power, and so you divide by 0.65 when you're integrating. Great, and so then this here is going to be the 9th outside, and then there's going to be 2 square boxes. First square box is when you put the upper limit in, so that will be 450 e 0.065 times 12 all over. Was there a minus sign on this? No, so this was exponential growth for people who know what that means. They're good at they've watched the previous videos and they know what exponential growth and decay are. 450 e to the 0.06. In the other box, you put in the lower limit now to the 3. And then over 0.065. And if you look at all that, that's all just a number, isn't it? So this is going to give the average value of this function from the periods of 3 to 12. So I'll type that into my calculator and I'll resume with an answer. Okay, so I'll pause the video. Yeah, so I typed that in there and I got 743.2. Okay. I don't know what that is. N might be something, it's bacteria, so that has units of bacteria. So on average from, say, this is 3 hours to 12 hours, there's 743 bacteria. Okay, so let's do a sanity check on that. So we should be able to use this formula here. We should know that when t is 0, that gives the initial amount of bacteria. So when t is 0, this becomes 0. And then this is e to the 0 is 1. So the initial amount of bacteria, n of 0, was 450. We then quickly type into a calculator what n of 3 was to see if that answer we got there a second ago, about 743 as an average. N of 3, this is like a sanity check here for yourselves in the exam. So multiply by 3. I am seeing that that works out as about 547-ish bacteria. And then at the 12th hour or whatever, just scroll across, calculator, and that works out as about 981 or 982, we'll round it, bacteria. And remember, so that's at the 12th hour, the bacteria is growing. And so we got a number there about 743 as the average over this 9 hours. And that looks pretty good because it looks kind of in between. So this is a good answer. That's a nice sanity check for us there. Only took a second and you can move on happy in the exam, you know. And then it says here, find the rate at which this is changing when t is 12. Give your answer correct. Okay, so that's easy. I'm sure everyone can do this. It's just dn dt, isn't it? The derivative of this is 450 does nothing. The exponential stays exactly the same. And then you just multiply by the derivative of the power, which is 0.065. Great, and you sub in 12. So 450 e to the 0.065 to the 12 multiplied by 0.065. I'm sure you can type that into your calculator, that's fine. For the sake of time, we'll move on. That would have had units now. We need to talk about units. So assuming t was in hours, that was dn dt, right? So I better get a number here. It asks us to interpret this. The interpretation is actually pretty good for you to learn about the interpretation. So I'll type that into my calculator and state the units. 450 E 0.065 by 12 multiplied by 0.065. So that works out, let me get a new color, we'll use blue. That works out as 63.8. Now that has units. N is in bacteria, T is in, we'll say hours. They didn't tell us what T was in. So then this is bacteria per hour. So what does it mean in the context of the question? It means that at the 12th hour, it looks like in the next hour there's going to be about 64 new bacteria. This is the rate, and it's positive as well. So it means the bacteria is increasing, and we're looking like at this moment in time, at the 12th hour, it looks like over the next hour we're going to get a 64 bacteria increase. It might be slightly more because this is what we call an instantaneous rate of change. It's not the average over the 12th and 13th hour. Hopefully that makes sense to people. Okay, great. After k hours, the rate of increase is greater than 90. Find the least value of k. Well, this is an interesting question. Okay, so and then there's a different colony. Okay, so this question has got interesting. So we'll snip this and bring this down here so that we can do this. Okay, so let's get our dn dt from before. dn dt. What did that work out as from before? We had, it was 0. I had it up there a second ago, so I'm just tidying it up from what we had. I just brought the 0.065. So that was DNG. We had it up a second ago before we subbed the 12 in. So in this, we're not subbing the 12 in. Find the rate after k hours. The rate of increase is greater than 90 bacteria. So we'll find out when this happens exactly, and then we'll deal with the greater than thing rather than writing a greater than symbol here. Okay. So we'll just do the algebra on this. So you can just divide by this under the 90. So you get e to the 0.065t equals 90 over 0.065 times 450. Now you can go if you want and write that in as a decimal in your calculator, but you can still move it around here for your logs. So the whole point of logs is to get the power on its own. So it'll be 0.065t on its own log. The base here is e, the base stays the base, and then that leaves room for this other thing, 90 over 0.065 times 450. And then in the next line, you'll just divide everything by this, all over 0.065. So I type that into my calculator. T equals, or they call it K, but I'll call it T for the minute. So T equals ln 90 over 0.065 multiplied by 450 over 0.065. Okay, so that allegedly happens at 17.29 hours, right? Now, in these questions, you got to be very careful. It's not just a matter around up or down, okay? And if you've watched my previous videos on these, just on the channel, you'll see to be very careful. And they love asking this type of question where you have to use logs, and the student is required to not just round up or down, but to think. Okay, there's two possible answers here. It can either be round up or round down. We need to check both of them. Okay, read very carefully what they want. Find the least value of k for when you go above 90 bacteria. So this is our dn dt formula up here, right? Sub the 17 in and then sub the 18 in, and let's see what happens, okay? So if we sub 17 in here for t, let's see, is it above or below 90? So 0.065 multiplied by 450 multiplied by e to the power 0.065 times 17. That works out as 88.31. Is that greater than 90? No, it's not. Okay, let's put the 18 in. You'd show all the workings for this, obviously, for the examiner. I'm short for time now, so I got to hammer it out. So you put the 18 in there, you get 94.24 bacteria per hour. Now the rate has gone greater than 90 bacteria per hour. So this happened when you're in the 18th hour. So the answer here is 18. Okay. So it was not a case of round down. It was round up. But they could have reworded this question where it was actually round down. And I'll tell you what it would have been reworded as if 17 was the answer. They would have said After k hours, the rate of increase is less than 90 bacteria per hour. Find the most value of k for when this happens. Okay, so the biggest hour you could put in there when the bacteria is still below 90 would have been the 17th hour. So that would have been the correct answer if it was worded the way I said there. And you can rewind the video for what I said. Okay, great. So you got to always check. You got to always check, you know, and the examiner is expecting you to check. Okay, the marking scheme could have deduct marks if the student didn't check and all they done was a lazy round up or down. Okay, so we have the number of bacteria in early stages of a different colony can be approximated by this other exponential, where P at T is bacteria and we're in hours. Assume both colonies start growing at the same time. Find the time when in both colonies are the same. Great. So we're going to just set two exponential functions together equal to one another, and I'll show you the algebra on this. So this isn't a differentiation question, this is just algebra. So pause the video and have a go at setting them equal to one another. See can you solve it. It's very important you know how to do this. This can come up in exams. So you set them equal to one another and you find t. You need to know how to solve it. I'd say there's a lot of students watching this video now that don't know how to solve this because this is tricky if you've never seen it done before. What you do is you bring all the numbers to one side and all the exponentials to one side. So we'll bring 450 over here. We'll bring the 220 under it. Divide both sides by 220. Leave this guy here and divide both sides by this guy. So he ends up underneath here. Okay. I'm sure people are okay with that algebra step. Now, these have the same base, so their powers actually take away. So this can be written as 450 over 220 is equal to e to the 0.17t minus 0.065t. Okay, and so then that basically means you can simplify that down. That's 45 over 22 is equal to e. What's 0.17 minus 0.065? It's 0.15 now. 0.105. 105 t, and then you can just use your logs from here to get it on its own. So I'll just do it quickly here. 0.10, I'll use another color. So you just want to get t now. 0.105 t equals log to the base e, base stays the base, and then that leaves room for this here, which is 450 over 220 as we had before. And so then t equals ln 45 over 22 all over 0.105. And these bacteria colonies have the same amount of bacteria at this moment in time. Let me type it in. 6.8 hours to the nearest hour. Yeah, so you would want to write here that t is 6.815 hours, and then they say round it to the nearest hour, and so you'll say 7 hours. Okay, so that's a really important trick here. This question comes up where two exponentials you have to set equal to one another, and you need to know how to do the algebra on it, and you divide both of these, take their powers away, and then you can use logs. Great. Flashcard for that, anyone who didn't know. Okay, so hopefully we're pretty close now to getting through this now. There's not going to be any more red marks. We've covered all the important questions you should know. So yeah, let's keep going here. So we're nearly there now. Let's find the next one. So we're skipping over a lot of these here because we've already kind of covered a question like them, you know. So I've picked out the important ones that give you a good variation of stuff that come up. So I picked this one here. We're nearly at the end of the documents. This is a trig function from 2015. These are really important because these are nice exam paper questions, you know. So I like these. If I was writing a paper, I'd be putting these on it because they revise both the paper 2 kind of trigonometry stuff, and you can also revise your algebra here, you know. But this could have came up on paper 2, for example, or paper 1. Anyways, f dash t. Give it a go there, everyone, of course. So the derivative of this goes to 0, and then we have 4.75 that doesn't do anything, just going to be there before and after. Sine goes to cosine, the inside stays exactly the same. And then we multiply by the derivative of the inside, which is 2 pi over 365. Okay, and yeah, you could tidy it up if you want, or you could just leave it like that. Hence or otherwise, find the length of the longest day in Galway. So what you got to do here, pause the video, obviously, give it a go. So the longest day, f a t models the length of the day, as you could imagine, okay? We're looking for the length of the longest day, so we want to maximize f of t. Now, there's two ways to do this. There is a fantastic otherwise here, okay? And I'm going to show you the fantastic otherwise after. But we're going to just do what the algebra expects us to know. If we want to maximize this function, the way we maximize f of t is we get its derivative and set it equal to 0 and find its maximum point. And we'll check it that we'll usually get 2 points, and we'll check if it's a maximum, because the second derivative test says that the second derivative should be less than 0 if you have a max. Right, so we want to maximize the length of the day. Right, so we then need to set this thing equal to 0. Now this is great because when this is 0, these numbers, you can just divide them out. So what we're really dealing with is a situation here where 2 pi t over 365 is equal to 0. Now this is an interesting thing. Just from your knowledge of trigonometry, you should know that there's 2 times from the unit circle. Okay, again, if the unit circle is rusty, you go look at them trigonometry. I have a really good video on this YouTube channel which just focuses on the unit circle. You should look at that. You should know, leaving cert higher level, that cosine, which is associated with the x value of the point that moves around the unit circle, has an x value of 0 when you're at, in radians, that's 90 degrees, but in radians, that's when theta is pi over 2, and also when theta is 3 pi over 2. So there's 2 solutions to this here. The answers to this are when this is the theta in here, so when 2 pi t over 365 equals the first one up here, which is pi over 2. Or there's the other solution, when we have 2 pi t over 365 equal to 3 pi over 2. And one of these will be the max and one of these will be the min. So I'll just very quickly just do the algebra on this. So then the pi's cancel, thankfully. The 365 comes up here and the 2 would go under there. So it's really 365 divided by 4. So 91.25 is one of them in days. And then the other solution over here is, you multiply across by the 365, cancel the pi's. So it's really 3 times 365 divided by 4. So yeah, it's 3 times this number basically. So it's 273.75. So one of these will give the max and one of them will give the min. So what we want to do now, you got to know which one gives the max or min. So you need the second derivative to test this. Okay, so we will get the second derivative here because this is what we're expected to do at leaving cert higher level. Leaving cert ordinary level, they do a really routine way of doing this. You can just put both of those t values into the original function, and whichever one gives the maximum value will be the one that is the max, you know. So they just trial and error the 2 things in. But there are unique scenarios where that actually isn't correct. Where like whichever, we're not going to get into that now, but there's a reason why at leaving cert higher level we're meant to be checking these who's max and min by using second derivative test, because this always works, and that just throwing the values in, checking who's a bigger value is not always the way to work out who's local max or min. Anyways, so let's get our second derivative. We'll take a derivative of this red function here. So cosine will become, so we'll just move our numbers out the front. They don't do anything. So we have a 2 pi over 365. Cosine becomes minus sine when you take a derivative of it. And then this is 2 pi t over 365. And then we multiply by the derivative of the inside, which is 2 pi over 365. So we really have 2 of them, so I'll put a squared there. Now all we got to do is put both our values in here. So if we go f dash dash 91.25, you put it in there for t, and then put in f dash dash 273.75, and you'll see one of them is positive and one of them is negative. So I'm going to pause the video and put both of them in there for t. Okay, so I put both of them in there, and the one that gives the negative value for the second derivative is the 91.25, and if the second derivative is less than 0, that means it's a max. So this point is associated with the max. So the longest day will occur when t is 91.25, and the shortest day occurs when t is 273.75. So you've basically got full marks in this question. All you need to do is actually work out what the longest day is. So put the time in when the longest day happens. So you put that in there. So you go F now, not F dash, not F dash dash. It's F we're subbing into here, 91.25. And you sub that in there. I'll just show the workings for this. Plus 4.7, and this will be your longest day. So this was a really good question here. And as I said, I expect something like this to come up in state exams because it's such a good revision of, do students understand their paper 2 trigonometry, and do they understand their first, second derivative tests, their calculus. So 12.25, make sure everything's in radians. Sine, and I'll show you how to do this without having done any of this using the or otherwise. Multiply by 91.25. So the longest day is 17 hours. That works out as exactly 17 hours, okay? That is the longest day. And as you'd imagine, it's less than 24 hours, as you'd imagine. Okay, there was actually a really smart way you could have done this, okay? Study this function. What part of it can actually change? There's only one thing that can change value, t, right? Now, that's located inside of a sine. Now, if you've done those videos on where I go through trigonometry, or especially the unit circle, sine cannot go and give a value of something like 30. It can't give a value of minus 10. Sine can only give values between what and what? Minus 1 and 1. So the absolute maximum value this thing could have ever given was a plus 1. Inside that red box, the biggest it could have ever given is a plus 1. Okay? Now think about it. We want to make f of t as big as possible because f of t is the length of the day. So if you want to maximize this function, let the sine take on the biggest possible value it can, which is a plus 1. And then all you got to do here is say that f of t is equal to this plus 4.75 multiplied by the biggest possible value this thing could give, which is a 1. And so you can see that 12.25 plus 4.75, 17 hours. And that's it. That'll be full marks. You just need to make it very clear to the examiner, and you'd write this out in words. The biggest possible value the sine can give is a plus 1. And then that'll be the scenario when you get f of t maximized. Full marks. Okay, that was a great question. Hopefully people can make a few interesting flashcards on that, okay? Yeah, I don't think there's any need to do this here. You can obviously do that yourselves. Use the integration to find the average value of the day in Galway over the 6 months. So you want to do integration there, as I had up there before. Remember the average value function where we go 1 over b minus a to b of our function with respect to whatever it is. So you'll be integrating this function 1 over your b minus a. They're basically telling you it here over the first 6 months. So a would be 0, and then this will be 184 days, something like that. Yeah. Or t. Actually, what was I writing there? Yeah, find the length of the. Find what day the length. Yeah. So t, f of t is in hours, but t is in days. Okay. So yeah. So I'm sure people get that. It's not too complicated. Okay. You're just using the average value function to integrate this here from 0 to 184. Yeah, and integrating that's routine enough. Okay. So we've already done a question on average value. You can rewind the video to that if you're scared of the average value function. You shouldn't be though. Okay, so let's go along here. I think I have at least, so this is a question I want to do. So the video is on an hour and a half now. Is there another one down here I picked? There is one final one down here. So this is a nice little question here. This is very rare. This kind of thing rarely comes up, right? And I love the text and test books, and they tell people how to get vertical asymptotes, but they don't tell them how to get horizontal asymptotes, okay? So it's a fantastic algebra question, this, and I'd love to see this asked some year, exactly as it is here now, and it's due to be asked because it's such a smart question. And this is all the way back in 2012 mock paper before kind of project maths. So pause the video, everyone, and give these a go. So asymptotes. what is an asymptote? An asymptote is when a function kind of gets really close to a value. So I'll give you an example here. So I say you had something like this, it leveled off there, and say there was a horizontal line here at a value of 3. The asymptote is the horizontal line. It's the y equals 3, and then this might be the function that's trying to get really close to the asymptote. So you have to understand who is the asymptote. The asymptote is the horizontal line that it's trying to get really close to. It's not the function itself. So one of the most common places that we see asymptotes is with something like, say, exponential decay. Say like the graph of e to the minus x, right? That looks something like this. Now, look at what it's doing. It's trying to get really close to the x-axis. And as you go all the way off here to infinity, it'll get really close to the x-axis. So basically all the way, when x goes off to infinity all the way to the right, then y will take on a value of 0, but only at infinity. And so this is getting really close to the x-axis, but who is the asymptote? It's not the function itself, it is the x-axis here. The x-axis is the horizontal line. So if you were asked, what's the equation of the asymptote here for this function? It's a horizontal asymptote, and it's the equation of the x-axis. And we should all know horizontal lines are defined by whatever y value they go through. And so the equation of the x-axis is just y equals 0. Okay, if that doesn't make sense, go look at the coordinate geometry of the line videos I have on the YouTube channel. So we should know a horizontal line, for example, that goes through 2 has an equation of y equals 2. A vertical line that goes through an x value of minus 3 has an equation as simple as x equals minus 3. That's the equation of vertical lines. Okay. So we have an unusual looking function here. So what a lot of people can do is they know how to get the vertical asymptote. The vertical asymptote is when the function blows up. So this function is going to blow up when you put 3 in for x, because you cannot have 0 on the bottom. If you have 0 on the bottom, you try and put 3 into this function here, you'll get 4 over 0. You try and type that in your calculator, it'll say error. So the function has blown up when x is 3. So if you put, so that's the vertical asymptote. So we know, and we're told to write down its equation. So x equals 3 is the equation of a vertical asymptote that this guy will have an issue with. So let's put the 3 over here. So this function is going to blow up here. And what it usually looks like is it'll blow up, it'll curl up really close to this, it'll go off to infinity, and then it'll shoot up from down here, okay? Right. There's another option. It could actually curl up towards it, it could curl down this way and then come down from here. So we have to actually draw a sketch of this, so we'll build this up. So if you've never seen a question like this, you're going to get great learning from this question and a great flashcard out of it. Okay, so yeah, this function blows up if you put a 3 in the bottom, so it has an issue at 3. Okay, now the horizontal asymptotes people don't know how to get, because even the text and test book doesn't go through how to get them. Right, to get a horizontal asymptote, you need to see what f of x's value is when x goes off to infinity. Okay, that tells us what the function is leveling off to, as you've seen there earlier on. Remember, when we go out to infinity, we see what y value it levels off to. Remember, e to the minus x leveled off at y equals 0, the x-axis. So where is this going to level off to? Well, when you want to get the limit of a function as x tends to infinity, you try and put infinity in first. And so you got like infinity plus 1 over infinity minus 3. So that's infinity over infinity. You can't have that. That's undefined. So that's not the way to do it. So the way you get a limit here is you divide above and below by the highest power of x. So what we'll do here is we'll divide everything by x, and you show the workings for the examiner like this. So this is revising limits. I've already covered a question or two like this. I think there was something to do with an n. There was a question like this anyways in previous parts on the YouTube channel where I'm doing differentiation tutorials. So we divided everything by x there. I've done the same thing top and bottom. And so that then works out as 1 plus 1 over x all over 1 minus 3 over x. Now you can do limit as x tends to infinity here. You can just put it in. So it's 1 plus 1 over infinity over 3 minus infinity. What's 1 over infinity? So in a new line here, you'd show that's 0 for the examiner, 3 over infinity 0, and so then this is 1. So this here levels off as you go all the way out to infinity to a value of 1. So it has a horizontal asymptote, y equals 1. Okay, and then if you want to find out where it's doing all the way off to the left, you check what happens when you put in minus infinity, and it'll be the same thing. If you put in minus infinity here, minus infinity, it's like 3 over minus infinity is still 0, and then it's like minus 0, but it's still 0, you know. So the horizontal asymptote is y equals 1. So we've established, we've got our thing here, the equations of the asymptotes are y equals 1 and x equals 3. Now we have to draw a graph of this. I'm just going to do, this would be the part 2 here, which draw a rough sketch of this. So there's two options, okay, and we'll draw it in Desmos after. You need to draw your horizontal asymptote, y equals 1 first. Okay, you could draw it either order, it doesn't matter. So that's y equals 1. And then you draw your vertical asymptote, x equals 3. Now there's two options that can happen here. So basically, the function can curl like this, and then it'll shoot up like that, and then it'll start coming up from up here and curl out here. That's option 1. Or it's option 2, where it curls down the way here, and then it comes down from up here and curls off, getting asymptote to this. See the asymptote behavior. Right, we need to work out which is which. And the way you do this is you just work out, are we above or below on one side of the line here? So what we're going to do is, we're going to just put an x value in here we'll see what it's doing on the y-axis here. Is it above or below when x is 0? That means you're on the y-axis. So if we put 0 in here for x, we see that y is equal to minus 1 over 3. So a point on this graph is 0 minus 1 over 3, a point on this function we're trying to plot. So we just got a point. Now where would we plot that? Where would we plot 0 minus a third? So that's like down here. It's below the thing, so minus a third, yeah. Okay, so that's a point in the graph. So we need to go through that blue point, so that can tell us which one we are. So let's rub out this option here. Let's rub out these dots. So we have to somehow go through that blue point and be an asymptote to the green lines that we sketched, knowing that the pink lines are the x and the y-axis, okay? So how do we do that? Let me see, that's minus a third, yeah, that's fine. So you could do it this way, like such, and that curls down that way, and then it's going to come down like this here. Probably too aggressively, it'll probably be a bit flatter, like that, something like that. So that's the function there. So basically what the examiners want to see, that you've done this kind of a bend up here, and then you've done this kind of a bend here. This is a very complicated question, but it can absolutely come up, and I hope that made some sort of sense to people there. So I'm gonna graph this in Desmos, and you'll see this kind of bend and this kind of bend. So I'll pause the video here and I'm gonna just graph that function in Desmos. Okay, so we're in Desmos, so I'm going to clear our workings away. So you can see I graphed the function there. It's doing exactly what we said it would do. And I'm going to I'm going to draw in the asymptotes, y equals 1, and then x equals 3. And look at it doing exactly what we've done. And I was able to sketch this just from, as I was building you through the knowledge points. And look, the examiner, it's got the bend here, and it's got this kind of bend here. And so we basically done it. So there you go, you get your first asymptote pretty easy. You just see where the function blows up on the bottom. It'll give a 0, and you can't have a 0 on the bottom. And so that means you've got your vertical asymptote, x equals 3. And then you got this horizontal asymptote of basically, what was it? It was a third, what did it? Yeah, it levels off at a y value of 1. See the red line leveling off at 1 as you move all the way out to infinity. See, it's getting closer to 1. Okay, so that is a really good exercise for people there, and it's a very rare past paper question. So hopefully you enjoyed that and you get a flashcard out of that. And if that comes up, you're a prepared student to know how to get vertical and horizontal asymptotes now, and then how to sketch the function by basically working out which behavior is it. Is it like a this and this, or is it like a this and this? And you just get 1 point to work out which one it is. Okay, show that it has no turning points. That's easy. So we just take a derivative of this and set it equal to 0 and show there's no solutions. So I'll just hammer that out here. F dash x. Now, the way I'm going to get that, this is obviously a quotient rule, but I've been shown before that you can do this using a product rule if you rewrite it like this. The video, we're getting close to the end now, guys. I know the video's on an hour and 40 minutes. So what we do here is we call u and uv. So then u equals x plus 1, v equals x minus 3 to the minus 1, du dx. This is also very important. You know, this kind of question comes up all the time. You got to be prepared. Du dx is 1. dv dx here, you multiply down by the power. You keep the inside exactly the same. Reduce the power by 1, multiply by the derivative of the inside, which is 1. And so when you tidy that up, that works out as minus 1 over x minus 3 squared. So sub this into your product rule, which is, you know, u dv v plus v du. Yeah, you know what the product rule is. You're all good with that. So u is x plus 1 times dv dx minus 1 over x minus 3 squared plus v, which is 1 over x minus 3 when you write it in its other format, and times du dx, which is 1. Now we're going to set all this equal to 0 because we're looking for turning points. So when I tidy this up, it is a minus x minus 1 on top here, all over an x minus 3 squared, plus a 1 over x minus 3 here, and that's all equal to 0. So we can write this as a single fraction here if we multiply this one above and below by x minus 3. And when you do that, the left side here will become, on top we'll have minus x minus 1 from here. Then we'll have a plus x and a plus minus 3. And then on the bottom, no need to multiply it out, we just go x minus 3 squared equals 0. The x's cancel, and on top you're just left with minus 4 over x minus 3 squared. That's equal to 0. Then you just multiply across by the bottom, and then you get minus 4 equals 0. And then this is like, therefore, no solutions. You know, minus 4 can't equal 0, and therefore no turning points. There's no turning points as there is no solution for f dash x equals 0. It just doesn't work. Okay, that'll be basically the examiner is looking for this and looking for this, and then that's full marks. And another thing as well, this is f dash x here, and you can see f dash x is always negative because the bottom is always positive if it's something squared, and this is always negative, so the function is always decreasing. And we can probably see that from Desmos. Look at this. See the y value here is decreasing, and then look, yeah, it does a jump, fair enough, but then it's, look, it's still always decreasing in value. Y is always decreasing, so very interesting. So one final question, one bonus thing to finish all this off for you. 2012 project maths here. State whether f is injective. Okay, so you should know what injective, surjective, and bijective is, people. Okay, and give a reason for your answer. So pause the video and have a go at that. So what's important here is we're talking about this in a closed interval. We're only interested in it from 0 to 5, right? So for something to be injective, right, we need to just revise what our injective, surjective is, okay? So let me get a bit of blank paper here I can do a little sketch on. Okay, so we should know about the horizontal line tests, right? So we'll take a linear line. A linear line is both injective and surjective. When you can draw all these horizontal lines, right? Injective wants you to hit it at most once, okay? Injective means you hit the function at most once, okay? That's injective, right? Surjective wants you to hit it at least once, okay? So am I hitting this at least once every time I go across? Yes, I absolutely am, right? So I'll give you an example of a function now that is neither injective or surjective. And I have a nice diagram for you to learn this as well. There's a quadratic. Now look at the issue with the quadratic. Look at this horizontal line. That missed it completely. Who's really not happy with that? Surjective is not happy with that. That needs you to hit it at least once. So this is not surjective. Look at this. This horizontal line hit it twice. So this is not injective. So a quadratic is neither injective or surjective, okay? So you'd be thinking a cubic. Well, a cubic is really just a, you know, it's just a quadratic continued. So then you'd be thinking the same kind of thing here. But you got to be careful. We're not plotting the full cubic. We're only plotting it from this range here, okay? And so the part A can inform people on certain things here with the max and the min value. So now that I've stated that, let me get up my little diagram. So I made a little diagram here for people to kind of make a flashcard on what I was on about there. So injective is this at most once thing, and surjective is this at least once. Okay, so let's rewind that back there so that that lines up with that. Yeah, so I got the wording right. Injective at most once, see that there, and surjective at least once. Okay, at least once. So you'd make a little flashcard for yourself on that. And if you're both injective and surjective, then you're bijective. Okay, so yeah, you can see there really nice wording on it. Bijective means you hit it exactly one hit. Okay, so this says at most one. This says at least one, and then this is exactly one hit. Okay, so pause the video and make a flashcard on that, of course, you know, because it's a very useful. So yeah, and then obviously give this a go now, and that diagram might help as well a little bit. Okay. Okay. So hopefully you gave that a go. So what we need to do here is we need to get a little bit of information from part A here. So injective is really, you could say, pissed off if this happens. If the function turns around and a horizontal line comes in and hits it more than once, okay, you're not injective if that happens, okay. Injective wants to hit the function, you know, at most once, okay. So there can't be any turns. The function cannot turn around. So the quadratic could absolutely be okay. The cubic here could be okay as long as it doesn't turn in 0 to 5. So we know cubics will go and do something like this, right? But if, for example, between here and here was 0 and 5, this thing absolutely would be injective because look at all my horizontal lines in here. They only ever hit it once. But where the problem would happen is this. If it does turn in the 0 to 5 range, so for example, if this is 0 and this is 5, there's two turns here, even if there was just one turn. The minute it turns around, a horizontal line will hit it twice. So this is a fantastic question, this, and it deserves to come up again, okay? So basically the student is using their information from here. If the function turns at all between 0 to 5 on the x, that means one of these turnarounds happens, and that means a horizontal line would hit the function twice. So we need to check the max and min values and where they occur. So we can just work out their x values. We don't have to actually get the full max and min coordinates. So we get f dash x here. So it's 3x squared minus 10x plus a 3. We set this equal to 0 to find the turning points, and we can factorize that. It will be a 3x times an x equals a 0. It'll probably be 1 and 3. It'll be nice and simple. 3 and 1, both negative. And so this function will turn around when x is a third and when x is 3. And that's completely busted the problem now because it doesn't matter who's max and min here. It means this function is turning around. This will be your explanation for the examiner. This function turns around at 3 and it turns around when x is a third. So that means, for example, when you're at the point 3 here, the function does a sort of U-turn here. Whether it's like that or whether it's like that, it doesn't matter. A horizontal line then will bust it twice. And if you hit it twice, you're not injective, you know. And I'll graph this in Desmos first, of course, so we can confirm this. So I'll pause the video. Okay, there's our guy. There's our function. And then we'll put the domain that we actually care about it in. So a vertical line through 0 and a vertical line through 5. Now, the reason I'm drawing those vertical lines is so this function does actually not exist out here in terms of this problem. This said that this function is only graphed between 0 and 5. So you see I'm putting white here. This function does not exist out here, and it'll stop then after the black line. So that's between 0 and 5. And now this is what we were on about. We can draw horizontal lines, and look what happens here. Bang, you hit it twice. You're not injective. Particularly down here. Remember it turned at 3, which we knew. I draw a horizontal line here, bang, because you turned around. No good, no good. You're not injective. If the domain, however, was between, that looks like 1, and this is 2.5, right? Okay. The function absolutely would have been injective, okay? Because it didn't turn around in that domain, and every time I draw a horizontal line within there, I only hit it once, so the function would have been injective. If the domain was between 1 and 2.5. But the domain was between 0 and 5, and so it turned around within there, so horizontal lines do crash into it more than once. Okay, that was a pretty fantastic question there, so Obviously make a flashcard on that and be aware of it. So there you go. That's the end of the video. So hour and 50 minutes. So there was a part 1 and part 2 to this, and you're really well covered for the kind of application questions that come up on differential calculus and also integration. There's a lot of integration stuff covered here. So yeah, so between the videos that are on the channel for differentiation and calculus, you're pretty well prepared for what will come up in your Leaving Cert higher level exam. Okay, thanks for watching. Be sure to subscribe and like and comment if this video helped you. Okay, thanks for watching.